Beneath Greenland's vast frozen expanse, mysteries endure, resisting decades of scientific study. Ancient Inuit stone structures, glaciers that fracture without warning, and hidden subglacial lakes hint at secrets both human and natural, challenging what we know about this remote land. Each discovery raises questions that refuse answers, leaving a lingering sense of unease across ice and tundra. Across jagged fjords and windswept plains, you will trace abandoned settlements, witness massive ice collapses, and encounter methane plumes rising from the hidden ocean floor. You will glimpse stone formations whose purpose remains uncertain, cracks that cleave glaciers into colossal islands, and frozen landscapes that preserve echoes of time long past. Every observation immerses you in Greenland's extremes, revealing a land where the ordinary yields to the unexplained. The camp century, nuclear tunnels beneath the ice. Far beneath the frozen surface of northwestern Greenland lies the remains of one of the most unusual engineering experiments of the Cold War. In the early 1960s, the United States Army constructed a hidden installation within the Greenland ice sheet, a labyrinth of tunnels carved directly into ancient ice and known as Camp Century. At the time, it was presented publicly as a remote scientific research station studying Arctic conditions, yet the project concealed deeper military ambitions that were only revealed decades later. Today, the tunnels have long since collapsed and vanished beneath shifting layers of snow and glacier ice. Even now, scientists cannot fully determine what remains buried there, or how the relentless movement of the ice sheet has transformed the hidden base. Construction of Camp Century began in 1959 in the remote northwestern region of Greenland, about 240 kilometers inland from the American Air Base at Thule. The project was operated by the United States Army Corps of Engineers with the permission of Denmark, which held sovereignty over Greenland but allowed American military operations during the Cold War. Engineers deployed enormous trench-cutting machines that sliced long corridors through compacted snow and ice. Prefabricated structures were lowered into these trenches and covered with arched roofs of steel and snow blocks. Once buried again beneath thick layers of ice, the installation became an underground settlement stretching several kilometers beneath the Arctic surface. Inside the frozen base, a surprising level of daily life took shape. The tunnels connected sleeping quarters, laboratories, workshops, storage areas, and communal spaces where soldiers and scientists could gather during the endless Arctic winter. Electric lights illuminated corridors carved directly from ancient glacier ice, and narrow passageways led to research rooms where scientists studied snow accumulation and the behaviour of the Greenland ice sheet. Temperatures outside could plunge below -40 degrees Celsius, yet inside the tunnels, the base functioned like a small subterranean town. For a brief moment in history, people were living and working inside one of the largest glaciers on Earth. Powering such an isolated settlement required an unusual solution. In 1960, the United States installed a portable nuclear reactor known as PM2A beneath the ice to generate electricity and heat for the base. The reactor was designed specifically for remote military locations where conventional fuel supplies would be difficult to maintain. Shielded within the underground tunnels, the nuclear system quietly powered the camp for several years, providing light, warmth and energy to laboratories operating deep inside the glacier. Few places in the world have ever hosted a nuclear-powered facility embedded directly within moving ice. At the same time that soldiers maintained the base, scientists carried out some of the earliest deep studies of the Greenland ice sheet. In 1966, researchers drilled an ice core that descended through more than 1.3 kilometers of ice before reaching the frozen bedrock beneath. Each layer of the core represented ancient snowfall compressed over thousands of years, preserving a detailed climate record stretching far into Earth's past. The discovery was groundbreaking, and decades later scientists would return to that same core to extract new information about ancient atmospheric conditions. Yet the deeper significance of Camp Century lay in a military concept that remained hidden from the public. The installation served as the testing ground for a classified plan known as Project Iceworm. Military strategists envisioned building a vast network of tunnels beneath the Greenland ice sheet that could conceal hundreds of nuclear missiles aimed toward the Soviet Union. These launch sites would be mobile, relocated periodically as tunnels shifted, making them nearly impossible for enemies to detect or target. Camp Century existed partly to determine whether such a system could function inside the constantly moving glacier. What engineers discovered during those experiments changed the fate of the entire project. Although the ice sheet appeared solid and permanent from above, conditions within the tunnels revealed something very different. The glacier was slowly flowing under its own immense weight, behaving less like stone and more like a thick river of frozen material. Within only a few years, the carefully carved corridors began to warp as the ice compressed and shifted around them. Ceilings sagged, walls bent inward, and passageways had to be repeatedly reshaped just to remain usable. The structures embedded inside the tunnels gradually tilted and sank as the surrounding snow compacted. Engineers quickly realized that maintaining a stable tunnel network within the ice would require constant reconstruction. Even the reinforced trenches of Camp Century, built with careful planning and heavy machinery, were gradually being crushed by the natural motion of the glacier. This slow deformation made the vision of a massive underground missile network increasingly unrealistic. By the mid-1960s, military planners quietly abandoned Project Iceworm, acknowledging that the ice sheet could not reliably support such an enormous and permanent infrastructure. Camp Century itself remained active only a short time after that realization. By 1967, the United States Army closed the base and withdrew its personnel from the site. The portable nuclear reactor had already been removed and transported away, but much of the base could not be easily recovered. Fuel supplies, construction materials, equipment, sewage, and various chemical wastes were left behind inside tunnels that were already beginning to collapse under the shifting glacier. At the time, officials believed the growing ice sheet would permanently entomb the abandoned installation. For decades, that assumption went largely unchallenged, as the buried base disappeared deeper within the Greenland ice sheet. Then, in 2016, a group of climate scientists studying Greenland's long-term ice behaviour revisited the location using modern climate models and satellite data. Their research suggested that the glacier might not remain permanently frozen over the site. If regional warming continues, surface melting could eventually penetrate deep enough to reach the level where the old tunnels were buried. The discovery raised a new and unexpected question about what exactly still lies hidden inside the drifting glacier. More than half a century after its closure, the remains of Camp Century are believed to be trapped within the moving ice sheet, slowly travelling toward Greenland's western coast, along with the glacier itself. The original tunnels have almost certainly collapsed under decades of pressure, scattering debris through layers of ice that continue to shift and flow. Scientists studying the region still cannot determine precisely where those remnants now sit within the glacier or how they have changed over time. The abandoned base was once designed as a secret weapon hidden inside the Arctic ice, yet today it has become something else entirely, an unresolved scientific puzzle drifting silently beneath Greenland's frozen surface. Somewhere deep within the Greenland ice sheet, the lost tunnels of Camp Century are still moving. The strange geometry of the Hiawatha impact crater. Radar images collected during surveys of Greenland's ice sheet eventually revealed an enormous circular formation hidden beneath the Hiawatha Glacier, a structure so symmetrical that scientists immediately recognized it as something unusual. The discovery emerged from airborne radar systems designed simply to measure the thickness of the ice sheet and map the shape of the land beneath it. Instead of a typical landscape of buried mountains and valleys, the instruments traced the outline of something far more distinctive. Beneath nearly a kilometre of ice appeared a nearly perfect ring. The geometry was so striking that researchers soon realised they were looking at one of Greenland's most puzzling hidden features, a structure now known as the Hiawatha impact crater. Airborne instruments designed to map the thickness of the ice began tracing faint curved ridges beneath the glacier that did not resemble any ordinary geological feature. These radar systems, carried aboard research aircraft flying long survey lines across northern Greenland, send radio waves through the ice and record the reflections from the bedrock below. Over the years of flights, the radar images began forming a pattern that looked remarkably circular. The ring appeared sharply defined compared to the surrounding terrain, and its symmetry stood out even through the distortions caused by the thick ice above it. What first looked like a subtle anomaly slowly revealed itself as something immense. Careful analysis of the radar data slowly revealed the full scale of the formation, showing a circular depression roughly 30 kilometers wide, buried under nearly a kilometer of ice. At that size, the structure would rank among the larger impact craters discovered on Earth. What surprised scientists most was not the crater itself, but the fact that it had remained unknown for so long. Greenland's ice sheet hides vast stretches of ancient terrain that no one has ever directly observed. Only with modern radar mapping have researchers begun to see the outlines of landscapes preserved beneath the glacier, and in this case, those hidden contours suggested something dramatic had once occurred there. The geometry of the structure immediately suggested a violent origin because its raised rim and central uplift closely resembled the signature of a meteorite impact. When large asteroids strike the Earth, the tremendous energy released excavates a circular cavity and pushes rock upward at the centre, creating a distinctive shape that geologists recognise around the world. Radar images of the Hiawatha structure revealed both of these features. Beneath the ice appeared a clear rim rising around the crater's edge, and a subtle uplift near the centre where the ground had rebounded after the impact. These patterns strongly indicated that a cosmic collision had once struck northern Greenland. Yet the most perplexing question surrounding the Hiawatha crater is not whether an asteroid struck Greenland, but when the collision actually occurred. Determining the age of an impact crater usually involves studying exposed rock layers or collecting samples directly from the site. In this case, the entire structure lies buried beneath a massive ice sheet, making direct investigation extremely difficult. Without access to the crater itself, scientists must rely on indirect clues such as sediments carried away by glacial rivers or patterns revealed by radar imaging. Those clues have produced competing interpretations that do not yet agree. Fragments carried by meltwater streams flowing out from beneath the glacier have provided scientists with rare physical clues about the buried structure. As the Hiawatha Glacier slowly moves toward the coast, meltwater flows beneath it and emerges at the glacier's edge, carrying sediment from deep below the ice. Among these sediments, researchers have identified grains of shocked quartz and other minerals that show evidence of intense pressure. Such minerals are commonly produced during meteorite impacts, when rock is subjected to enormous forces within fractions of a second. Their presence strongly supports the idea that a large asteroid once struck the region. Because the crater lies sealed beneath a massive ice sheet, researchers must reconstruct its shape indirectly through radar reflections and scattered mineral evidence. Every radar survey adds new layers of detail to the picture of the buried landscape. These images show channels carved by subglacial rivers, ridges of rock pushed upward by the impact, and sediment deposits that may have formed as debris settled after the collision. Yet even with these tools, scientists are studying a landscape they cannot see directly. The crater remains hidden beneath ice that has likely covered it for thousands of years. Different scientific teams have proposed competing timelines for the impact, each interpretation suggesting a very different story about Greenland's past. Some researchers believe the crater may be relatively young in geological terms, possibly forming during the last ice age, when large ice sheets already covered much of the northern hemisphere. If this interpretation is correct, the impact could have interacted with the ice itself, melting enormous volumes of frozen water in a short period of time. Other scientists argue that the crater may be far older, formed long before the modern ice sheet developed and later buried as glaciers expanded. Some researchers have even considered whether such a collision could have disturbed the surrounding ice sheet or influenced regional climate patterns. A large asteroid striking near or beneath a glacier could release tremendous heat and energy, potentially producing sudden floods of meltwater and sending debris across the surrounding landscape. If the Hiawatha impact occurred during a glacial period, it might have temporarily reshaped the local environment. Yet geological evidence for such events remains uncertain, and scientists continue to debate whether any wider consequences can be linked to the crater. Adding another layer of uncertainty, radar surveys later reveal the possibility of a second buried impact structure not far from Hiawatha. Known as the Patterson crater, this formation appears less clearly defined, but may represent another ancient collision hidden beneath the same ice sheet. The presence of two large impact structures in relatively proximity raises intriguing questions about Greenland's geological history. It also reminds researchers how much of the Arctic landscape remains unexplored beneath layers of ice that conceal the terrain below. Despite years of study, the Hiawatha crater remains a landscape that no human has ever directly seen. Its rim, central uplift, and buried debris exist only in radar images and fragments of minerals carried out by meltwater streams. The glacier above it continues to flow slowly across the hidden structure, grinding and reshaping the terrain with each passing century. For scientists studying Greenland's ice sheet, the crater represents a reminder that the frozen surface conceals events that unfolded long before modern observation. Beneath the ice lies a record of ancient catastrophes that the glacier still refuses to fully reveal. Whatever struck Greenland left behind a perfectly circular scar, now hidden beneath nearly a kilometre of ice, and the glacier still refuses to reveal when that moment truly happened. The vanishing settlements of the northeastern colony. Records hint at a once thriving community along Greenland's southern coast, yet the northeastern settlement vanished in the 15th century with no explanation preserved in written history. Archaeological evidence shows that farms, churches and burial grounds once dotted the fjords, yet centuries of snow, wind and ice have hidden much of their exact locations. Historians and archaeologists have long puzzled over why the colony, which once seemed stable and connected to broader European trade networks, gradually disappeared without any record of catastrophe or forced evacuation. The mystery persists because the usual explanations for societal collapse, war, famine, disease, leave little trace in this remote Arctic region. When Eric the Red and other Norse settlers arrived from Iceland around 985 CE, they carved farms and small villages into fjordside land that seemed both remote and promising. The fjords offered sheltered harbours, access to grazing lands, and proximity to the sea for fishing and seal hunting. Settlers cleared the rocky soil for pastures, raised livestock, and built turf and stone dwellings capable of withstanding long winters. Although Greenland's climate was harsher than Iceland's, the early settlers adapted quickly, importing knowledge and techniques suited for cold coastal living and developing a society that blended survival skills with European social and religious practices. Over the following centuries, the colony grew into a network of hundreds of farms, accompanied by churches and halls, revealing a surprisingly organised settlement for such an isolated region. Archaeological surveys have identified the remains of at least 16 church sites, including stone-built halls large enough for community gatherings. Farmsteads were spaced to maximise grazing land and fishing access, while allowing for communication along the fjords. Artefacts from the period indicate connections with Norway and Iceland, suggesting trade in goods like iron, cloth and timber. The eastern settlement, though remote, functioned as a self-sufficient society with social hierarchies and religious institutions mirroring those of medieval Europe. Daily life demanded relentless labour, herding sheep and cattle, hunting seals along icy shores, gathering driftwood, and carefully rationing imports of iron and other essential goods from Europe. Winter months were particularly harsh, with long periods of darkness and bitter cold forcing settlers to preserve food and maintain shelters against storms. Archaeological remains show that households stored hay, bone tools and dried fish in anticipation of lean periods. Even routine tasks required coordination and foresight, and failure to manage resources effectively could mean starvation or collapse, highlighting the fragility of life on the edge of the Arctic world. A wedding recorded at Hvalsey Church in 1408 marks the last known historical event involving the Norse settlers, after which the written record abruptly falls silent. The church's stone ruins are still visible today, standing as the final confirmed site of organised Norse activity in Greenland. No subsequent records from Europe or Greenland mention the settlement, raising questions about why such a significant community disappeared without note. The absence of documentation suggests either a rapid depopulation, gradual migration, or social collapse that left no chroniclers behind, a mystery that continues to challenge historians and archaeologists alike. Later expeditions from Norway discovered deserted farms and abandoned tools, yet no documents or eyewitness accounts explain why the population disappeared entirely. Ships arriving decades after the last records found houses empty and fields overgrown, with personal belongings left behind as if the inhabitants had planned to return. While some farms show signs of minimal maintenance after abandonment, there is no evidence of violent destruction, fire or widespread disease. The emptiness itself became a puzzle. How could hundreds of people vanish from a region they had cultivated and lived in for generations? Archaeological excavations have unearthed empty dwellings, scattered animal bones, and household items left in place. suggesting a gradual departure rather than a sudden catastrophe. Researchers have found tools, utensils, and even remnants of clothing indicating that the Norse left possessions behind, perhaps anticipating a temporary absence that became permanent. The settlement pattern shows no signs of conflict or mass death, leaving a haunting impression that the inhabitants simply walked away. These findings challenge assumptions about medieval colonization and survival in extreme climates, emphasizing that disappearance can be as mysterious as destruction. Climate shifts during the Little Ice Age likely strained agriculture and grazing, but evidence indicates that the Norse had endured severe winters long before without vanishing. Ice cores and tree ring data suggest cooling periods that shortened growing seasons and increased storm frequency, but the eastern settlement had persisted through comparable conditions in previous centuries. While environmental stress may have contributed to difficulties, it cannot fully account for the total disappearance. Scholars continue to debate how climate, combined with other factors, might have influenced the settlers' decisions to leave or abandon their communities. Trade networks with Europe collapsed over time, depriving the settlers of critical supplies such as iron and timber, increasing their vulnerability and isolation. Norse Greenland relied on ships from Norway for metal tools, building materials, and luxury items, and the decline of European interest in the distant colony left them increasingly self-reliant. Without iron for farming implements, ship repairs, or construction, even basic survival became challenging. The breakdown of trade would have compounded hardships already imposed by the climate, contributing to a slow unravelling of social and economic structures that once sustained the colony. Interactions with migrating Inuit groups may have influenced Norse survival, but the exact nature of these encounters, hostile or cooperative, remains largely speculative. Archaeological evidence shows the Inuit were present in southern Greenland during the Late Norse period, and some items suggest possible trade or cultural exchange. At the same time, differences in technology and subsistence methods may have created tension or competition for limited resources. The absence of definitive records leaves the impact of these interactions uncertain, adding another layer to the mystery of how the eastern settlement disappeared without a trace. Ultimately, the eastern settlement appears to have faded quietly from Greenland's fjords, leaving structures and artifacts behind while the people themselves vanished from the historical record. The disappearance was not marked by fire or sudden collapse, but by a slow erosion of presence. Farms were abandoned, livestock left behind, and churches fell silent. Modern researchers are left to interpret fragmentary evidence, from roof timbers preserved under sod to stone walls weathering centuries of wind and snow. Despite decades of study, the story of the Norse eastern settlement remains unresolved, a ghostly narrative of people who simply ceased to be seen. Along Greenland's southern fjords, the last Norse settlers departed their homes, leaving only silence and questions that the coastline has carried for centuries. The unidentified structure beneath the Greenland ice sheet. Scientists first noticed the anomaly while analysing ice-penetrating radar data, an unusual shape beneath the Greenland ice sheet that defied explanation. The surveys were initially part of routine mapping of the bedrock beneath the ice, but the patterns returned by the instruments hinted at something extraordinary. Unlike other known subglacial features, this formation displayed a degree of symmetry and scale that left researchers puzzled. The structure stretches for tens of kilometres, yet its outline does not correspond to any known geological or glacial process. Even preliminary interpretations of radar reflections suggested that there was more hidden below than anyone could initially imagine, a secret buried in ice for millennia. Measurements indicate the formation spans an extraordinary area, with contours and angles that do not match surrounding bedrock or typical glacial patterns. From the radar data, scientists could see a ring-like configuration, almost geometric in nature, interrupted only by the slow, shifting pressure of the ice above. The structure rises and dips in ways that distinguish it from the natural undulations carved by glaciers over thousands of years. Its scale alone challenges conventional understanding, suggesting a feature that could not have formed from ordinary ice movement or sediment accumulation. Each line of data seemed to deepen the mystery rather than offer clarity, hinting at a hidden history locked away beneath kilometers of frozen terrain. Signals from the radar suggest multiple internal layers within the structure, hinting at a complexity far beyond a simple geological deposit. The reflections indicate variations in density and composition that are difficult to reconcile with typical bedrock or glacial ice. Scientists note that some layers appear sharply defined, while others fade into diffuse patterns, creating a sense of depth and compartmentalization previously unseen in subglacial studies. These layers raise questions about the formation's origin, whether it resulted from unusual geological processes, repeated natural events, or forces that remain unknown. Each new analysis seems to reveal a feature within a feature, complicating the picture further. Geologists studying the region have found no natural process, glacial movement, tectonics, or volcanism that fully accounts for the formation's unusual profile. Greenland's bedrock has been extensively mapped, and while ice flow and erosion can create many strange shapes, nothing in the known geological record matches the precise angles and proportions of this anomaly. Researchers have considered the possibility of ancient volcanic activity or extreme subglacial melting, but evidence for such events is absent. The mystery persists because the formation appears deliberately distinct from the chaotic patterns normally produced by ice and rock interacting over time. Early hypotheses range from a subglacial lake to remnants of ice-distorted rock, yet none can convincingly explain the anomaly's symmetry and scale. Some scientists have speculated that unusual pressure points beneath the ice could create radar reflections resembling structure, but follow-up surveys fail to support this. Other suggestions involve rare forms of sediment accumulation or even natural crystal formations within the bedrock, yet these explanations remain largely theoretical. The anomaly challenges conventional thinking precisely because it combines features that are both massive and precise, leaving researchers with more questions than answers. Attempts to gather physical samples, including sediment cores and ice-embedded debris, have returned intriguing but inconclusive data, leaving the mystery largely intact. Meltwater streams and subglacial drilling have provided fragments of rock and ice that do not fully match known local geology. Some materials suggest high pressure or unusual mineral composition, hinting at forces beyond ordinary glacial processes. Each recovered sample offers tantalizing clues, while simultaneously deepening uncertainty, as nothing collected so far definitively identifies the formation. The ice shields the structure from direct observation, leaving only indirect evidence for interpretation. Unlike the Hiawatha crater or other known subglacial features, this structure exhibits patterns that resist classification within any recognized category of natural formations. Its edges curve and intersect in ways that suggest deliberate shaping, yet no historical evidence supports human involvement. No impact debris has been identified, and there are no signs of volcanic activity, leaving it with neither a crater nor a vent. Scientists are forced to consider possibilities that challenge established geological frameworks, weighing the anomaly against everything known about Greenland's frozen interior. It exists as an enigma, a feature that seems designed to defy explanation. Instrument readings reveal unexpected physical properties, from unusual reflectivity to anomalous density, suggesting the formation interacts with technology in ways researchers do not fully understand. Radar signals behave unpredictably in some regions, reflecting more strongly or fading without a clear reason. Gravity measurements indicate mass concentrations that cannot be easily explained by conventional bedrock structures. Magnetometer surveys show minor deviations that hint at localized mineral anomalies. Each of these measurements confirms that the formation is not simply a feature of the ice above it. Something about its composition or structure fundamentally differs from the surrounding terrain. If the structure is natural, it could represent an extreme geological event previously unrecorded. If artificial, it raises questions that science cannot yet answer. Its scale, internal layers, and unexpected physical properties leave room for speculation, but researchers remain cautious, unwilling to conclude without direct observation. The ice has preserved this anomaly for perhaps tens of thousands of years, and every probe into its depths only emphasizes how much is unknown. It is a formation that sits at the intersection of the known and the inexplicable, where conventional science brushes against the limits of understanding. Debates among researchers remain heated, with some advocating caution and others speculating freely about the potential origins hidden beneath the ice. Conferences and journal articles brim with arguments over whether the anomaly is an extreme but natural formation, a product of unusual glacial mechanics, or something entirely unprecedented. Each study raises new questions. How did it form? Why does it exhibit such precise layering? Could it be evidence of unknown subglacial processes? While conclusions remain elusive, the anomaly continues to draw attention from geologists, glaciologists, and curious minds worldwide. For decades, no human has penetrated the ice to witness the formation directly, leaving its true nature locked away beneath layers of frozen history. Drilling remains technically challenging, and remote sensing, while detailed, provides only partial insight. Every expedition must contend with the Greenland ice sheet's thickness, instability, and remote location, leaving the formation inaccessible. Its secrets remain entirely protected by the ice above, and the structure continues to hold its mysteries, silently resisting every attempt at explanation or direct observation. No probe, no drill, and no satellite has yet unveiled the full form of the structure, leaving Greenland's frozen interior to guard its secret from all who search. The puzzling dark zone of the Greenland ice sheet. An area within the central Greenland ice sheet drew attention when repeated satellite scans produced inconsistent signals that no one could initially explain. Researchers first noticed unusual readings while monitoring ice thickness and subglacial topography for mapping purposes, yet the dark zone behaved unlike any other surveyed region. Instruments returned erratic data. Some signals appeared as diffuse blurs, while others vanished entirely, leaving blank patches in otherwise continuous coverage. Scientists quickly realized that the anomalies were not errors, but indications of a region resisting conventional observation. The very concept of a portion of the ice sheet that confounded decades of monitoring sparked intrigue, inviting scrutiny from multiple disciplines. The zone stretches for several kilometers, yet its borders appear irregular, shifting subtly with each new survey, as if the ice itself resists precise measurement. Remote sensing maps show that the dark zone is neither circular nor linear, but fluctuates in shape depending on the time of year, temperature, and satellite angle. Its edges seem to dissolve into surrounding ice, creating a liminal space between detectable and undetectable. Survey teams attempting to trace the perimeter report minor variations in slope and density that complicate efforts to define the feature. This instability challenges conventional glaciology, raising questions about whether the phenomenon is seasonal, structural, or the product of unknown subglacial forces. Measurements from radar and LiDAR instruments reveal erratic reflections, sometimes returning diffuse echoes, and other times vanishing entirely, leaving researchers uncertain of what lies beneath. Radar signals penetrate the ice in ways that should provide predictable readings, yet here they scatter, refract, and occasionally produce false positives. LiDAR scans from aircraft similarly fail to resolve clear surface patterns, suggesting that the anomaly may involve a combination of surface and sub-ice factors. Researchers have considered ice density variations, air pockets, or liquid channels as potential explanations, but no single factor can account for the full range of observed irregularities. Each instrument seems to hint at complexity, yet fails to offer a definitive interpretation. Glacial flow within the region behaves unpredictably, moving at rates and angles that contrast sharply with surrounding ice, defying the patterns established over decades of observation. GPS sensors embedded in ice cores show acceleration in some areas, deceleration in others, and occasional lateral shifts that cannot be explained by topography alone. The behavior of the ice suggests that forces beneath the surface may be exerting influence, potentially from hidden meltwater channels, variations in bedrock friction, or previously unknown geothermal anomalies. These irregularities disrupt models that predict ice movement across Greenland and complicate forecasts of ice sheet stability, adding urgency to the mystery of the dark zone. Occasional glimpses of the zone from aircraft reveal faint optical effects, reflections, shadows, and subtle distortions that hint at something unusual under the frozen surface. Pilots report seeing darker patches of snow that do not match the surrounding albedo, sometimes extending for miles in irregular shapes. At certain angles, sunlight appears to shimmer differently, and photographs occasionally capture slight colour shifts or low-contrast gradients. These visual phenomena reinforce the idea that the dark zone is not merely a product of instrument error, but a feature with measurable physical properties. Yet even repeated flights fail to reveal any solid formation, leaving observers to interpret subtle optical cues while the ice conceals its secrets. Field teams venturing into the area have recorded temperature variations and snow density anomalies that do not align with expected seasonal or meteorological patterns. Handheld sensors and probes detect microclimates within the zone, with ice layers slightly denser or looser than surrounding regions. Snow compaction varies unpredictably, sometimes softening over short distances and other times hardening unexpectedly. These discrepancies make traversing the area difficult and prevent consistent measurement, forcing researchers to rely on indirect observations. Every expedition confirms that the dark zone is not uniform and cannot be fully understood through conventional fieldwork alone. Geologists have examined bedrock maps and subglacial surveys, yet no known formation, channel, or tectonic feature fully accounts for the phenomenon observed in the dark zone. The underlying bedrock appears relatively consistent with nearby regions, lacking the depressions or ridges that would explain unusual ice flow. Subglacial channels or lakes have been proposed, but sonar and radar do not detect continuous bodies of water beneath the ice. Even subtle geological anomalies fail to account for the scale, irregularity, and unpredictable behavior of the zone, leaving a gap between what is observable and what can be explained using standard glaciological models. Comparisons with other anomalies, such as impact craters or subglacial structures, highlight the zone's uniqueness. It lacks a discrete shape, appearing more as a diffuse and elusive phenomenon than a solid object. Whereas craters like Hiawatha reveal clear geometric features and subglacial structures like Camp Century are bounded and measurable, the dark zone defies these classifications. It is ephemeral in many senses, detectable primarily through indirect measurements and inconsistently visible through optical observation. Its existence is confirmed only through repeated anomalies in otherwise reliable instruments, making it a subtle, almost ghostly presence in the ice sheet. Opinions among scientists differ sharply, with some suggesting the irregularities result from instrument limitations, while others argue for unknown ice sheet dynamics operating beneath the surface. Some researchers maintain that the zone is a product of optical illusions, radar interference, or data processing artifacts, citing similar anomalies in other polar regions. Others insist that recurring patterns and correlations across multiple instruments suggest a real physical feature. The divergence in interpretation has fueled ongoing study, as each expedition and survey seems to raise further questions rather than resolving the mystery. If confirmed as a genuine feature, the dark zone could provide new insights into subglacial physics, ice behavior, or the complex interactions between ice and bedrock, long hidden from observation. Understanding the anomaly might refine models of glacial movement, reveal previously undetected microclimates, or uncover hidden processes at the icebed interface. Yet for now, these possibilities remain theoretical, constrained by the inability to observe or access the zone directly. The scientific significance of the dark zone is enormous precisely because it challenges existing frameworks, suggesting that even the well-studied Greenland ice sheet retains mysteries beyond current knowledge. Efforts to study it more closely remain constrained by Greenland's extreme environment, leaving the zone largely inaccessible and its full nature unresolved. Harsh temperatures, unpredictable weather, and logistical challenges make extended fieldwork difficult, while heavy equipment risks altering or damaging subtle anomalies. Remote sensing has expanded understanding, but it cannot fully penetrate the layered complexity that the ice conceals. Every measurement adds to the intrigue, reinforcing the sense that the dark zone is a phenomenon that exists at the edge of human observation, a puzzle frozen in place yet in constant flux. No matter how many satellites pass overhead or sensors probe its depths, the dark zone continues to elude understanding, its frozen secrets flickering at the edge of scientific knowledge. The mysterious Greenland subglacial lakes. Unusual radar signals first alerted scientists to the existence of liquid water beneath Greenland's frozen surface, revealing pockets that seemed impossible to exist in such extreme conditions. Researchers initially dismissed some of the readings as errors, but repeated surveys confirmed that these subglacial lakes were real, hidden reservoirs of water maintained in darkness beneath kilometers of ice. Their discovery challenged conventional understanding of the ice sheet, suggesting that vast, unseen systems of liquid water could persist under pressures and temperatures once thought inhospitable. Each new survey revealed more anomalies, deepening the mystery and igniting curiosity about what conditions might allow these lakes to endure. These lakes vary in size, with some spanning tens of kilometres, while others appear as smaller pockets, scattered in irregular patterns across the ice sheet's interior. Mapping the distribution has proven difficult, as their boundaries shift subtly in response to ice movement and seasonal pressure changes. Some lakes appear isolated, while others may be connected through hidden channels or pockets of meltwater, though the extent of these networks remains speculative. Their uneven distribution suggests a complex interplay of thermal, geological and hydrological factors that governs their formation and persistence, a combination that scientists have yet to fully understand. Despite the extreme pressure and near-freezing temperatures, the water remains liquid, insulated by the overlying ice and potentially warmed by geothermal heat from below. Ice cores extracted near suspected lake sites indicate slightly elevated temperatures compared with surrounding regions, hinting at localized heat sources or friction from glacial flow. The pressure at these depths suppresses freezing, allowing water to remain fluid even under conditions that would solidify it near the surface. This unexpected persistence of liquid water under seemingly unyielding ice has become a focal point for research, as it raises questions about how life and chemical processes might survive in isolation. Seismic surveys and ice-penetrating radar have mapped their contours, yet measurements are often inconsistent, reflecting the difficulty of detecting fluid bodies hidden beneath solid layers. Some surveys suggest the presence of depressions or subtle undulations in the bedrock beneath the lakes, while others detect only a diffuse echo with no clear shape. The variability has led to competing interpretations, with some scientists emphasizing the limitations of instrumentation and others suggesting genuinely irregular lake shapes. These conflicting data points contribute to the sense of the lakes as elusive, dynamic entities, resisting easy categorization and leaving researchers to infer their nature from partial evidence. Hydrologists note that water moves slowly between interconnected lakes, creating subtle influences on ice flow and surface elevation that challenge conventional glacial models. Meltwater channels, pressure-driven flows, and intermittent subglacial drainage may connect these bodies in ways that are invisible to surface observation. Ice sheet models incorporating these hidden currents reveal that even small shifts in water volume can affect the speed and direction of glacial movement above. The influence of subglacial water on ice dynamics adds a layer of complexity, suggesting that these lakes are not only scientifically fascinating, but may play a role in the long-term stability of the Greenland ice sheet. Chemical analysis of ice cores above these lakes reveals traces of unexpected minerals and solutes, suggesting that the subglacial water may possess unusual geochemical properties. Elevated levels of dissolved salts, organic compounds, and trace metals hint at processes occurring in isolation from the surface. The presence of these substances raises questions about how long the water has remained trapped, how it interacts with the surrounding rock, and whether these chemical conditions could support microbial ecosystems. Each discovery deepens the intrigue, implying that the lakes are not merely pools of water, but potentially active environments shaped by unseen forces over millennia. Researchers speculate that microbial life could survive in these isolated lakes, enduring millennia of darkness and extreme conditions, hinting at ecosystems entirely cut off from the surface. Studies of Antarctic's subglacial lakes have revealed bacteria capable of metabolizing nutrients in total darkness, and similar life may exist beneath Greenland's ice. If microbes do inhabit these lakes, they could provide a glimpse into how life adapts to extreme isolation, offering insights into biology under conditions akin to other icy worlds in our solar system. The possibility of hidden ecosystems adds a profound dimension to the mystery, bridging geophysics, chemistry, and biology. Compared with Antarctica's subglacial lakes, Greenland's appear more fragmented and shallow, yet they present equally puzzling thermal and hydrological behaviour. Whereas Antarctic lakes like Vostok are larger and more uniform, Greenland's water bodies are scattered and irregular, sometimes partially frozen at the edges while maintaining liquid cores. Their dynamic nature, combined with the rapid movement of the overlying ice, creates a situation in which the lakes are transient yet persistent, challenging conventional models of subglacial stability. Scientists remain cautious, knowing that each measurement may capture only a moment in the lake's long and hidden history. Interpretations of the lake's origin remain contested, with some proposing meltwater accumulation over time and others suggesting ancient trapped water preserved beneath the ice sheet. Geothermal heat, friction from ice flow, and localized pressure gradients may contribute to their formation, but no single factor explains the variety of lake sizes and distributions. Some researchers posit that the lakes are remnants of a warmer period in Greenland's past, sealed beneath advancing ice, while others emphasize ongoing hydrological processes. The true genesis of these bodies of water remains one of the most intriguing puzzles in glaciology, resisting definitive explanation despite decades of study. Understanding these hidden waters is critical, as their dynamics may subtly influence the stability and movement of Greenland's vast ice sheet in ways still poorly understood. Subglacial lakes can act as lubricants for glacial flow, accelerating ice movement and affecting downstream meltwater discharge. Their presence also complicates models used to predict ice sheet response to climate change, suggesting that hidden processes beneath the ice may be as important as surface temperatures or snowfall patterns. Each discovery reinforces the idea that the Greenland ice sheet is a complex living system in which unseen waters quietly shape the frozen landscape above. Direct observation remains nearly impossible, leaving the lake's full scale, structure, and secrets to be inferred from indirect measurements and cautious speculation. No probe has yet penetrated these depths without risk of contamination, and logistical challenges make physical study extremely difficult. Satellite and radar measurements provide tantalizing glimpses, but each method offers only a partial picture. The lakes remain a ghostly presence beneath the ice, hinting at hidden worlds that persist in darkness, isolated and enigmatic as researchers continue to map, measure, and theorize. Below kilometers of ice, these hidden lakes endure, silently shaping the Greenland ice sheet, while keeping their ancient secrets beyond the reach of every probe. The Lost WWII aircraft beneath the glacier. A faint metallic outline first appeared in aerial photographs, hinting at a long-forgotten aircraft trapped deep within Greenland's ice. Initially dismissed as shadows or anomalies in the snow, repeated imaging eventually confirmed that something solid lay hidden below, defying expectations of what the glacier might conceal. The discovery sparked curiosity among historians and scientists, drawing attention to a long-lost chapter of World War II aviation and the challenges of locating objects entombed by centuries of ice and shifting snow. Each new image suggested not only the presence of an aircraft, but also the possibility of well-preserved components frozen in isolation, a silent witness to history. The plane was part of a small fleet assigned to transatlantic patrols and reconnaissance during World War II, vanishing without a clear explanation during one mission. Records indicate that aircraft were dispatched across Greenland to monitor enemy activity, deliver supplies, and survey weather conditions critical to Allied operations. Yet some planes never returned, leaving their fates largely unknown, except for fragmentary reports of crashes or last known positions. The Greenland ice sheet, with its treacherous terrain and unpredictable weather, claimed countless missions, creating a veil of mystery over these vanished aircraft that persisted for decades before technology allowed researchers to detect them. Gradually, snowfall and glacial flow swallowed the aircraft, folding its wings into the shifting ice and concealing it from all surface observation. Layers of accumulation compressed the fuselage and embedded the wreckage in a frozen matrix that preserved its form while making it invisible from above. The relentless motion of the ice transported debris slowly along the glacier, leaving it in positions far from its original crash site. This natural preservation, paradoxically, is both a safeguard against decay and a barrier to discovery, as the shifting glacier continues to distort and hide the plane from any would-be explorers or investigators. Ice-penetrating radar and satellite surveys eventually detected irregular echoes, confirming that something solid and anomalous lay hidden beneath the frozen surface. The radar signatures revealed shapes suggestive of wings and fuselage sections, though interpretation remained complicated by surrounding ice structures. Some images suggested intact components, while others resembled scattered fragments, creating debate about the true state of the aircraft. Each survey deepened the mystery, as instruments could detect the presence of metal and density differences, but could not convey the condition of internal systems or the aircraft's original configuration. Remarkably, sections of the fuselage and engine components remain preserved, encased in solid ice that has shielded them from decay for generations. Corrosion is minimal, and the cold, stable environment has slowed chemical reactions that would otherwise deteriorate metals and composites. Instruments, gauges, and wiring may still exist in recognizable form, frozen in a moment of history that the glacier has held in stasis. This unexpected preservation has drawn interest not only from historians, but also from engineers, eager to study wartime technology sealed away in a natural freezer. Reaching the site presents extraordinary challenges, as researchers must navigate crevasses, brittle ice, and shifting snowfields to even approach the aircraft's location. Helicopters can land only in limited areas, and ground teams face hours of travel across unstable surfaces. Weather conditions frequently interrupt operations, and sudden whiteouts can render travel impossible. The combination of remote location, physical danger, and environmental constraints has limited direct study to brief, cautious reconnaissance, leaving most knowledge derived from remote sensing and historical inference. Examination of recovered fragments could reveal details of wartime engineering, materials, and design that are otherwise lost to history. Components such as engines, navigation instruments, and communication equipment may provide insight into the technological capabilities of the period. The preservation of these parts allows for comparisons with museum examples or archival records, offering a rare opportunity to verify historical documentation. Each fragment could help reconstruct the plane's last mission, illuminating decisions, challenges, and mechanical failures that contributed to its disappearance. Glacial movement has slowly altered the aircraft's orientation, causing uncertainty about the precise location and complicating any potential recovery efforts. Over the years, the ice may have rotated, sheared, or partially buried the wreck further, shifting debris from its initial crash configuration. Small movements can make locating specific sections difficult, while larger flows may have transported fragments beyond the immediate site. Understanding these dynamics is crucial for planning any retrieval mission, as misjudging ice movement could result in failed operations, or even loss of parts that may never be recovered. Interpretations of radar returns remain debated, with some experts questioning whether the detected shapes represent intact planes, scattered debris, or natural rock formations. The glacier itself produces complex reflections that can mimic metallic structures, creating ambiguity in remote sensing data. While most researchers agree on the presence of at least one aircraft, details about its size, orientation, and condition continue to spark discussion. The conflicting assessments highlight the difficulty of studying artifacts in extreme, inaccessible environments and underscore the limits of current technology in solving the mystery fully. Stories of the lost aircraft have captured the imagination of historians and explorers alike, fueling speculation about the missions, crews, and circumstances that led to its disappearance. Letters, mission logs, and survivor accounts provide fragmented glimpses into operations over Greenland, but none clarify the plane's ultimate fate. Public fascination grows as each new survey or potential discovery is reported, and the aircraft has become emblematic of the broader enigma surrounding wartime aviation in remote and hostile regions. Its story intertwines human courage, technological ambition, and the unforgiving power of nature. The aircraft still lies inaccessible within thick ice, leaving its full story and perhaps long-hidden artifacts locked in frozen silence. Remote studies provide tantalizing hints, but no certainty, and every expedition faces the same unyielding barriers of cold, depth, and shifting ice. Each radar echo, each satellite image, adds to a picture that remains incomplete, preserving the mystery as an unresolved chapter of history that resists closure. Greenland's relentless ice holds the lost aircraft in silence, a frozen witness to history whose secrets remain sealed by time and ice. The enigmatic stone ruins at Hvalsey. Scholars remain puzzled by the sudden disappearance of Hvalsey's Norse inhabitants, as the settlement's stone ruins offer no clear explanation for why life abruptly ended there. Archaeologists and historians have long examined the site, yet even with modern techniques, the community's final days remain shrouded in uncertainty. The ruins, consisting of sturdy houses and a finely built church, suggest a well-organised settlement capable of withstanding harsh conditions, yet evidence of abandonment appears sudden and complete. Some artefacts hint at daily routines abruptly interrupted, while skeletal remains show no obvious sign of violent conflict. which Hvalsey endures as a frozen riddle, its story only partially recoverable from the stones themselves, archaeologists have noted that Hvalsey is remarkably well preserved compared with other Norse sites, with its church, houses and stone walls offering an unusually complete glimpse into medieval Greenlandic life. Unlike smaller or partially eroded settlements, Hvalsey provides a rare opportunity to study the social structure, architecture and material culture of the Norse Eastern colony. Every carefully fitted stone, from the foundations to the church walls, conveys the skill and labour invested by its inhabitants. Items left behind, from tools to domestic objects, form a tangible connection to human lives lived centuries ago, creating an intimate yet mysterious window into history. The settlement was part of a network of Norse communities established around the 10th and 11th centuries, thriving on farming, hunting and trade, yet the reasons for the eastern colony's eventual disappearance remain unclear. Greenland's eastern colony was smaller than the western settlements, and evidence suggests residents engaged in similar activities, raising livestock, harvesting fish, and occasionally trading with Europe. The harsh environment demanded resilience, and Hvalsey's stone buildings reflect an understanding of structural durability and adaptation to wind, cold, and seasonal challenges. Despite these preparations, the colony ultimately vanished, leaving scholars to piece together fragmentary records and environmental clues. Hvalsey Church, constructed from carefully fitted stones, contains inscriptions that chronicle family events and local affairs, providing rare insights into the daily lives and social structures of its inhabitants. Gravestones record births, marriages and deaths, hinting at the rhythms of a once thriving community. These inscriptions suggest social cohesion and adherence to shared traditions, yet they also provoke questions. Why did such a seemingly stable settlement suddenly empty? The church remains one of the last tangible links to the lives of the Norse Greenlanders, offering both a sense of intimacy and a haunting absence. Exposure to harsh Arctic weather and the relentless erosion of the coastal cliffs would have created constant challenges for residents, yet the settlement endured far longer than many historians expected. Winter storms battered the coastline, snow and ice accumulated against homes, and fjords froze and thawed unpredictably. Even with careful planning, these forces likely strained the settlement's resources, influencing decisions about migration or survival. Yet Hvalsey's ruins indicate long-term occupation, suggesting resilience that makes its abrupt desertion all the more enigmatic. Tools, household items, and fragments of clothing unearthed in archaeological surveys suggest an active and skilled community, while skeletal remains hint at both ordinary life and possible hardship, leaving questions still unanswered. Knives, spindle whorls, and cooking implements speak to domestic labour and craftsmanship, while animal bones reveal diet and hunting practices. Human remains show evidence of disease, minor injuries, and malnutrition, but nothing conclusive points to the reason for abandonment. Each discovery adds pieces to a puzzle that still resists full explanation. Historians have proposed a range of explanations for Hvalsey's disappearance, from famine and disease to climate shifts or migration to more hospitable regions, but no single theory fully accounts for the settlement's abrupt end. The Little Ice Age may have begun affecting Greenland, shortening growing seasons and threatening food security. Epidemics could have spread quickly through tightly knit communities, while isolation made assistance or trade difficult. Migration toward western settlements or other areas of the island is plausible, yet records of such movement are scarce. Each hypothesis leaves gaps that maintain the site's aura of unresolved mystery. Excavations over the past century have gradually revealed details about the layout, craftsmanship, and daily routines of Hvalsey's residents. Yet the ultimate fate of the community remains a compelling enigma. Archaeologists have mapped house foundations, reconstructed building techniques, and catalogued artifacts with painstaking care. Soil samples, pollen studies, and carbon dating provide additional context for diet and environmental conditions. Nevertheless, the sudden departure of an apparently thriving community resists explanation, and every excavation uncovers further questions alongside the answers. The settlement's isolation, cut off by fjords and ice-laden terrain, may have contributed both to its survival and to the enduring mystery surrounding its sudden desertion. Distance from other colonies could have provided safety from conflict, but also limited access to vital resources. Harsh seas and unpredictable ice made travel treacherous, intensifying the stakes for any decision to leave or remain. Hvalsey's location ensured preservation of its structures over centuries while also hiding clues that might clarify why its population vanished. Hvalsey has inspired sagas, oral traditions, and scholarly speculation alike, drawing human imagination towards stories of vanished families, unrecorded journeys, and lives interrupted by forces beyond their control. Folklore recounts dramatic storms, lost children, and enigmatic disappearances, while historians debate the extent to which such tales reflect reality. The combination of myth and material evidence amplifies the settlement's aura, making it a site not just of historical importance, but of lingering narrative intrigue that continues to engage both scientists and storytellers. Extensive study has yet to unravel Hvalsey's secrets, its silent stone walls guarding the details of a vanished community that left behind more questions than answers. Modern technology, satellite imaging, geophysical surveys, and forensic analysis has illuminated aspects of daily life, construction, and diet, yet none can fully explain the abrupt departure of its residents. The absence of written records from the final years deepens the mystery, leaving the site a rare example of a civilization paused mid-story, preserved in stone and memory. The weathered stones of Hvalsey endure, silently guarding the unanswered questions of a community that vanished into Greenland's unforgiving coast. The sudden collapse of Greenland's ancient ice streams. Unexpected fractures have appeared along Greenland's oldest ice streams, defying predictions and leaving scientists baffled by the sudden accelerations and collapses recorded in recent decades. These colossal rivers of ice, flowing for thousands of years, were once considered remarkably stable, their movements measured in predictable, slow increments. Yet satellite imagery and field surveys reveal instances where ice streams accelerate unexpectedly, carving vast icebergs into fjords in a matter of weeks. Such events challenge assumptions about glacial physics, prompting questions about internal mechanisms and the unseen forces at work beneath the ice. The suddenness of these collapses evokes a sense of both awe and unease among the glaciologists who monitor them. These ancient rivers of ice, some flowing for millennia, once moved with remarkable stability, carving fjords and valleys while preserving a silent record of climatic history. Ice cores extracted from the Greenland ice sheet show layered sequences recording centuries of snowfall, temperature shifts, and atmospheric composition. Within this frozen archive, there is evidence of long-term consistency in flow patterns, yet modern observations reveal a striking deviation from these historical norms. The contrast between the documented stability of the past and the erratic behaviour of the present heightens the sense of mystery surrounding Greenland's ice dynamics. Glaciologists monitor these colossal sheets using satellites, radar mapping, and field expeditions, yet even the most advanced instruments cannot fully reveal the hidden dynamics beneath kilometres of ice. Ground-penetrating radar provides glimpses of subglacial topography, revealing valleys, ridges, and ancient sediments that influence ice movement. GPS sensors track surface motion, while ice-penetrating drones and remote instruments attempt to measure basal flow and sub-ice water presence. Despite these technological advances, many processes remain invisible, occurring deep below layers of compacted snow and ice, hidden from direct observation. Several ice streams have shown abrupt retreats or rapid disintegration, often within mere months, providing dramatic evidence that long-term stability can collapse in ways that remain unexplained. For instance, certain streams along the southeast coast have accelerated suddenly, disgorging large icebergs and leaving behind destabilized ice fields. These abrupt shifts are not uniform. Neighbouring streams may continue flowing at normal rates, suggesting that triggers are localized, complex, or otherwise elusive. The scientific community continues to document these anomalies, seeking patterns that might clarify why some streams collapse while others persist. Researchers have proposed multiple mechanisms, including subglacial meltwater lubrication, uneven bedrock topography, and shifts in internal ice pressures, though none fully accounts for the unpredictable nature of these events. Meltwater accumulating at the base can act as a lubricant, hastening flow, yet observations do not always correlate with sudden collapses. Bedrock shape influences channeling and stress distribution, but similar topographies produce differing behaviours. Internal ice deformation and stress propagation may contribute, though models remain incomplete. Each hypothesis adds nuance without fully explaining the erratic behaviour, leaving the phenomenon shrouded in uncertainty. The extreme environment presents immense challenges. Sensors freeze, access is limited, and even comprehensive datasets leave crucial gaps in understanding the forces at work. Field teams navigate crevassed terrain, battling sub-zero temperatures and unpredictable weather, often risking weeks in remote conditions for measurements that cover only tiny fractions of the ice sheet. Remote sensing bridges some gaps but cannot capture every variable influencing ice dynamics. The combination of logistical difficulty and scientific complexity ensures that Greenland's ice streams retain an aura of inscrutability. Their sudden collapses as enigmatic as they are consequential. Sudden collapses reshape glaciers, produce massive calving events, and disturb nearby fjords, demonstrating that these ancient ice streams are far more dynamic than their apparent solidity suggests. Ice cliffs hundreds of meters high can fracture violently, releasing icebergs that drift into the ocean, sometimes impacting shipping lanes or marine ecosystems. Glacial lakes form and drain unpredictably, and fjord water levels fluctuate in response to newly liberated ice masses. Each dramatic event underscores the latent power contained within the ice, a reminder that what appears frozen and static may, in fact, be in constant unseen motion. Patterns observed across neighbouring ice streams often contradict one another, with some exhibiting stability, while others collapse under similar conditions, defying conventional glaciological models. In regions where multiple streams converge, some maintain centuries-old flow rates while adjacent channels accelerate inexplicably. These inconsistencies challenge predictive models and highlight gaps in understanding basal hydrology, stress transmission, and ice rheology. The scientific debate is heightened by the unpredictability of outcomes. A single parameter shift can trigger localized instability without affecting surrounding ice, leaving researchers cautious in concluding. Scientific debate rages over the timing, causes, and potential precursors of these collapses, emphasizing how Greenland's ice sheets continue to resist complete explanation. Conferences, publications, and simulations attempt to parse the data, yet divergent interpretations remain. Some scientists argue that subtle climate oscillations are sufficient to destabilize certain streams, while others emphasize the role of subglacial topography or previously unrecognized glacial processes. These discussions illuminate both the depth of knowledge gained and the persistence of mysteries, reinforcing the sense that Greenland's ice sheets are still writing their own story in real time. Understanding these sudden shifts carries profound implications for predicting sea level rise and modelling the future behaviour of polar ice under changing climates, yet uncertainty remains pervasive. Accelerated iceflow contributes directly to global ocean levels, while calving and meltwater affect ocean circulation and local ecosystems. Current models incorporate these collapses only partially, leaving projections vulnerable to sudden, unforeseen contributions from destabilized streams. The unpredictability of these events underscores the fragility of assumptions about ice sheet stability and the importance of continued observation and research. Ongoing study has yet to uncover the forces behind these sudden collapses, leaving scientists to witness Greenland's ice streams as they seemingly defy all expectations. Each new event reminds researchers that these rivers of ice are not simply passive participants in the climate system. They're active agents capable of dramatic, unforeseen movement. The intersection of history, environmental science, and natural mystery converges here, in the silent yet powerful motion of ice that has endured for millennia, yet continues to surprise and challenge human understanding. The ancient ice, long thought steady and predictable, now moves with a silent, unstoppable force that refuses to reveal its secrets. The strange sounds recorded beneath Greenland's ice. A series of low-frequency vibrations detected deep beneath the Greenland ice sheet has confounded scientists who cannot trace their origin to any known glacial process. The recordings first emerged during radar and seismic surveys aimed at understanding basal ice movement, yet what should have been routine data instead revealed enigmatic hums and pulses. These signals seemed neither random nor fully explained by conventional glaciology, prompting a mix of curiosity and unease among researchers. Over time, the sounds became more distinct, their patterns revealing a complexity that suggested a source unlike any previously documented within ice sheets, leaving the scientific community questioning what exactly they were hearing. Specialized sensors, including seismic arrays and hydrophones, were deployed across multiple ice streams to capture these subglacial acoustics in unprecedented detail. Engineers designed instruments to survive sub-zero temperatures, high pressure, and layers of shifting ice, often deploying them through boreholes drilled kilometers deep. The data collected allowed for both frequency analysis and spatial mapping, offering clues about the direction and depth of the vibrations. Each deployment, however, revealed new challenges. Instruments occasionally failed, recordings were interrupted by interference, and the sheer scale of Greenland's ice made it difficult to distinguish local anomalies from broader patterns. Initial recordings revealed irregular pulses and hums, sometimes lasting for hours, whose patterns resist correlation with melting, crevassing, or other observable ice activity. Some sounds appeared as low rumbles, others as high-pitched oscillations, producing a sonic landscape both strange and haunting. Analysts compared these recordings against known glacial noises, from basal sliding to iceberg carving, yet many signals persisted without explanation. The irregularity of their occurrence, sometimes continuous for days, sometimes punctuated by silence, added to the challenge of interpreting them and intensified the sense of a mystery lying deep under the ice. Natural explanations, such as basal melting, ice cracking, and subglacial water flows, account for some of the signals, yet certain anomalies persist without plausible causes. Meltwater moving under high pressure can create vibrations, and ice flexing under its own weight produces characteristic sounds, but none of these fully match the recordings. Even in areas where ice movement is well understood, certain pulses defy classification. The discrepancy between what should occur according to physical models and what is actually recorded continues to perplex glaciologists, suggesting that Greenland's ice contains processes still largely invisible to science. Geographic mapping shows clusters of these sounds recurring in specific sectors, suggesting that their sources are not evenly distributed but somehow tied to hidden features beneath the ice. Some locations produce frequent repeating hums, while nearby regions remain silent. The clustering hints at underlying structures or dynamics, potentially related to subglacial cavities, ice layering, or unexpected hydrological channels. Such spatial patterns provide tantalizing hints that the ice is not a uniform block but a complex resonant system, capable of producing sounds that remain impossible to attribute definitively to any known mechanism. A subset of these signals exhibits properties that do not match any documented glacial or seismic phenomena, leaving researchers puzzled and cautious in their interpretations. Some hums persist at unusual frequencies, while other pulses seem synchronized across distant locations, implying a connected process that current understanding cannot explain. Attempts to reproduce the sounds experimentally have failed, and even computational models offer only partial insights. Each new recording deepens the mystery, emphasizing that Greenland's ice is not merely a passive environment, but an active medium producing acoustic signatures that challenge conventional science. Scientific debate continues over potential explanations, including previously unrecognized ice dynamics, geothermal activity, or the influence of trapped subglacial cavities. Some propose that sudden shifts in basal stress propagate acoustic waves, while others suggest interactions with geothermal hotspots. Yet these ideas remain hypothetical, often inconsistent with observed patterns. The lack of consensus underscores the limits of current glaciology and highlights how much remains unknown about processes occurring beneath kilometers of ice. Discussions at conferences and in publications are often framed with caution as researchers confront phenomena that defy standard scientific models. Environmental extremes, signal interference, and the sheer inaccessibility of the ice sheet complicate attempts to model and interpret the acoustic data accurately. Boreholes can freeze, instruments can drift under ice movement, and electronic interference can create false positives. Researchers must painstakingly differentiate between noise, instrument artifacts, and genuine subglacial sounds. Even with sophisticated filtering techniques, some signals remain ambiguous, their true origin obscured by the challenges inherent in working within one of Earth's harshest environments. Some experts suggest that these elusive sounds may be indicators of hidden stress and movement within the ice, hinting at instability that cannot be seen from the surface. If certain zones of the ice are shifting or sliding unexpectedly, they might transmit vibrations detectable only through sensitive equipment. These acoustic cues could represent precursors to calving events, sudden ice flow changes, or unknown basal interactions. Observing the sounds provides scientists with a rare, indirect glimpse into processes otherwise invisible, hinting at a dynamic world under the frozen exterior that is full of movement, tension, and unknown potential energy. Historical accounts of singing glaciers and anomalous vibrations in other polar regions provide context, but Greenland's recordings differ in both scale and consistency. While mountaineers and explorers have reported glacier hums and moans for centuries, modern instrumentation shows that Greenland's subglacial acoustics operate on a magnitude and complexity unmatched elsewhere. The sounds are not seasonal or anecdotal. They are measured phenomena, systematically recorded, often repeating yet defying precise explanation. Comparisons to historical reports reinforce the notion that ice has long carried voices of its own, yet Greenland's manifestations remain uniquely baffling. Continuous monitoring has failed to identify the true source of these sub-ice sounds, leaving scientists listening in awe to vibrations from a hidden world. Each new detection reinforces the sense that the ice sheet itself is an enigmatic communicator transmitting low-frequency messages whose meaning and origin remain inaccessible. Researchers can document the patterns, map their intensity, and theorize potential causes, but the ice resists all attempts at complete understanding. Its hidden acoustics act as both evidence of activity and a reminder of the limits of human perception in extreme environments, where sight is limited and sound becomes a primary messenger of mystery. A haunting resonance lingers within Greenland's ice, carrying secrets that refuse to reveal themselves. The disappearance of the medieval Western settlement. Once a thriving cluster of farmsteads and churches along Greenland's western coast, the Western settlement mysteriously vanished, leaving little more than scattered stone foundations and untold questions for historians. Archaeologists have long marvelled at the scale of its disappearance, noting that while the eastern settlement endured for centuries, the western community seems to have simply dissolved from the historical record. Archaeological layers reveal the presence of sheep, cattle, and barley, alongside evidence of fishing and hunting, painting a picture of a society that had adapted, at least temporarily, to the challenges of the Arctic edge. Yet for all the clues in stone walls and field boundaries, the settlement's final days remain invisible, a ghostly absence that invites speculation but offers no certainty. Archaeologists examining the remains of longhouses and burial sites have pieced together fragments of daily life, revealing how residents farmed, hunted, and adapted to one of the harshest climates on Earth. Excavations have uncovered hearths, storage pits, and the skeletal remains of humans and livestock, each layer telling a story of human ingenuity and environmental pressure. Tools made of iron, bone, and antler hint at a self-sufficient community capable of surviving the extremes of Greenland's short summers and long, dark winters. Yet even as these physical traces emerge, they provide little explanation for why the settlement's population abruptly disappeared, leaving structures intact but abandoned. Medieval records, including trade logs and church documents, hint at population fluctuations and the settlement's ties to distant Iceland and Norway, yet they offer no definitive clue about its disappearance. Ships from Norway may have delivered timber, iron and grain, supporting subsistence in this marginal landscape, while letters and tithing records reveal a functioning ecclesiastical system. Still, after a certain point in the 14th century, the documents fall silent. There is no mention of emigration, famine, or violent attack. The written record aligns with the archaeological void, a community vanishing almost entirely from both memory and material evidence, as though the ice and wind had claimed it without a trace. Climate data drawn from ice cores and tree rings indicate a period of cooling and environmental stress, suggesting that harsher winters and shorter growing seasons may have challenged the community's survival. The onset of the Little Ice Age brought lower temperatures, increased storm activity, and reduced arable land. Grain cultivation became more difficult, livestock struggled in the increasingly harsh environment, and even hunting could not reliably offset scarcity. While environmental stress alone may not fully explain the disappearance, it likely intensified the fragility of a settlement already living at the edge of ecological possibility. Evidence of dwindling grazing land and soil depletion points to resource scarcity implying that the settlers faced mounting pressure to maintain livestock and sustain crops, yet no single factor fully explains their fate. Fields show signs of overgrazing, and repeated tilling may have eroded topsoil, reducing fertility. Bones from cattle and sheep indicate a decline in herd size over time, suggesting that feeding livestock became increasingly difficult. Yet even as subsistence faltered, the suddenness of abandonment in some sites hints at a trigger beyond gradual environmental decline, a catalyst that left homes and possessions untouched. Isolation amplified the settlement's vulnerability, as long distances from other Norse communities and limited contact with traders may have exacerbated both material and psychological strain. The western settlement was separated from the eastern settlement by treacherous fjords and glaciers, with resupply or rescue dependent on precarious maritime journeys. The combination of environmental challenges and geographic isolation may have intensified social stress, yet it is not enough to explain why one settlement disappeared while others persisted. The silence that followed has echoed through centuries, leaving no eyewitness accounts and only fragments of a vanished life. Some artifacts, including partially used tools and abandoned household items, suggest a sudden departure rather than a gradual decline, raising questions about what might have forced such an abrupt exodus. Cooking implements sit near fireplaces, and some homes still contain personal effects, implying that inhabitants left quickly, perhaps in response to an unforeseen threat. Yet no mass graves, scorched ruins, or signs of violence accompany these abandoned objects. The abruptness of the departure adds a layer of mystery, a human-scale puzzle juxtaposed against the slow, relentless processes of ice, wind, and erosion. Scholars continue to debate competing hypotheses, from migration to disease outbreaks or violent conflict, each plausible yet ultimately inconclusive in accounting for the settlement's complete disappearance. Some propose that the population moved westward, perhaps joining other communities or seeking new farmland, while others suggest epidemic or famine might have decimated residents. Archaeological and climatic evidence support fragments of these ideas, but nothing fully reconciles the sudden, total abandonment with the patterns of survival elsewhere in Greenland. The debate continues, but resolution remains elusive, reinforcing the settlement's status as an enduring enigma. Material culture provides subtle hints about daily routines, social organisation, and adaptation strategies, yet the abrupt cessation of activity leaves an unsettling void in the historical record. Household items, agricultural tools, and religious artifacts suggest a community attentive to both faith and subsistence, capable of sustaining itself despite environmental pressure. Yet after a certain point, traces of food storage, livestock management, and domestic life disappear. The silence is as telling as the artifacts themselves, marking the boundary between what is known and the unknowable fate of a vanished population. Modern techniques, such as ground-penetrating radar and isotopic analysis of skeletal remains, have illuminated settlement patterns and diets, yet the central enigma, why the community vanished, remains unsolved. Advanced imaging reveals longhouse foundations, roads, and field terraces, while isotopic studies indicate that inhabitants consumed both domesticated and wild resources. Each innovation in archaeological research adds nuance to our understanding of how the community lived, yet these insights deepen rather than resolve the mystery of disappearance. The puzzle is not a lack of data, but the inexplicable absence of closure. Centuries of research have yielded clues, insights, and theories, but the Western settlement's final chapter is missing, leaving only remnants and silence where a once vibrant society thrived. Even as archaeologists continue to uncover layers of habitation, nothing accounts for the sudden disappearance of its people. Unlike the Eastern settlement, which lingered into the 15th century, the Western community evaporated from both the human record and the landscape itself. The settlement survives only in foundations, scattered artifacts, and haunting questions that refuse to be answered, a puzzle frozen in time and memory. The Western settlement endures only in ruins and whispers, a vanished world that refuses to reveal the fate of its people. The hidden canyon beneath the Greenland ice sheet. An extraordinary anomaly deep within Greenland's ice first emerged in satellite data, revealing a massive canyon whose existence continues to puzzle scientists. Unlike surface features, this gorge is concealed beneath kilometers of ice, its sheer walls and winding valleys invisible to the naked eye. Researchers were initially skeptical, questioning whether such a structure could exist beneath an ice sheet as vast and uniform as Greenland's. Yet repeated surveys confirmed the findings, exposing a labyrinthine subglacial feature that challenges conventional understanding. The canyon's size, orientation and depth have inspired both awe and frustration, leaving questions about its origin and influence unanswered. Its sheer walls and winding valleys extend over distances so vast that even advanced models struggle to capture their full scale. The canyon appears to stretch tens of kilometers, with sections plunging hundreds of meters below the surrounding bedrock. Branching corridors twist unpredictably, creating a subterranean network that seems almost deliberately complex. Some areas appear narrow and channel-like, while others open into wider chambers where ancient ice layers have preserved unique geological histories. The interplay between rock, ice and hidden water creates a terrain that is difficult to measure, much less interpret, leaving scientists grappling with the limitations of current technology and knowledge. Geologists are particularly intrigued by the canyon's potential to illuminate the long-term evolution of the ice sheet, though its origins remain unresolved. The feature may record events from tens of thousands or even millions of years ago, preserving evidence of glacial flows, meltwater pulses and tectonic shifts. Understanding its formation could provide insight into how Greenland's ice responds to climate cycles and internal dynamics. Yet every attempt to fit the canyon into existing models raises more questions than answers, as it exhibits unusual branching patterns and abrupt depth changes unlike anything observed in other subglacial formations. By integrating seismic profiles, gravity measurements, and ice-penetrating radar, researchers have begun assembling a tentative picture of its hidden structure. These methods reveal not only the canyon's dimensions, but also subtle variations in bedrock composition and hidden channels that may have guided its formation. Satellite altimetry allows scientists to detect minute surface depressions corresponding to the canyon below, while seismic readings suggest zones where water may still flow beneath the ice. The combination of these techniques paints a picture of a landscape both alien and intricately connected to the ice above, yet it cannot fully explain how or when the canyon formed. Hypotheses about its formation range from sudden meltwater events in ancient warm periods to slow tectonic adjustments beneath the ice. Some scientists suggest that enormous volumes of subglacial water once surged through these channels, carving the canyon with force and speed, leaving behind deep grooves and complex branching patterns. Others argue that tectonic activity may have fractured the bedrock, with subsequent glacial erosion amplifying the canyon's depth and shape over millennia. Neither explanation is entirely satisfying, and both leave unanswered questions about the timing, scale, and environmental conditions that created such a hidden marvel. Small subglacial lakes and channels feed into the gorge, suggesting a dynamic network of water that continues to influence ice movement today. These hidden streams may lubricate the ice above, guiding its flow in ways that are difficult to model or predict. Researchers speculate that pockets of liquid water within the canyon could preserve ancient sediments and microbial life, effectively creating isolated ecosystems sealed away from sunlight for eons. Yet direct exploration remains impossible, leaving these subterranean waters enigmatic and largely theoretical, reinforcing the canyon's reputation as one of Greenland's most confounding mysteries. Its unusual branching patterns and depth challenge expectations, making it unlike any subglacial canyon previously mapped elsewhere in the world. While ice sheets in Antarctica and elsewhere conceal similar features, none exhibit the combination of scale, complexity, and hidden water channels found here. The canyon's shape does not follow predictable glacial paths, and some branches appear to cut across the underlying topography in defiance of gravitational logic. This irregularity has fueled intense debate within the scientific community, as traditional models fail to explain why the canyon diverged from what might be expected from ice flow and meltwater erosion alone. Scientists debate whether its features formed incrementally over millions of years or as a consequence of more abrupt geologic forces. Layered sediment trapped within its walls provides tantalizing hints of ancient ice ages, floods, and volcanic events, yet interpretations remain speculative. Some argue for slow, gradual carving by subglacial water over millennia, while others point to evidence of catastrophic pulses or sudden tectonic shifts that could have rapidly created major portions of the canyon. Each hypothesis reveals new complexities and contradictions, underscoring the limits of human understanding and the challenges of studying landscapes hidden beneath thick, shifting ice. Investigations hint that pockets of microbial life might survive in the canyon's hidden waters, offering glimpses of isolated ecosystems sealed away for millennia. If such life exists, it would persist in total darkness, under immense pressure and in near-freezing conditions, surviving solely on chemical energy from rocks and sediments. These potential ecosystems could provide insight into how life adapts to extreme environments, paralleling discoveries in Antarctic subglacial lakes. Yet no direct samples have been retrieved, leaving speculation as the only guide and ensuring that the canyon remains both a geological and biological enigma. Models indicate that the canyon may subtly direct ice flow and meltwater paths, yet its precise impact on the ice sheet's stability remains unknown. The channels and depressions beneath the ice sheet may accelerate or divert ice movement in unpredictable ways, influencing Greenland's contribution to global sea level rise. Scientists continue to refine simulations, but even the most sophisticated models cannot fully capture the canyon's hidden complexity. This uncertainty highlights the canyon's role not just as a scientific curiosity, but as a potential factor in climate dynamics, a reminder that what lies beneath can have consequences far beyond what we can see. Even with cutting-edge mapping and decades of study, the canyon remains a vast and enigmatic scar, its full story still beyond human comprehension. Its scale dwarfs any human exploration, and the interplay of ice, water and rock continues to challenge assumptions about subglacial processes. Each new study seems to reveal more questions than answers, deepening the sense of mystery that surrounds it. For now, the canyon exists as a silent monument to ancient forces, hidden from view yet shaping the ice sheet above in ways scientists are only beginning to grasp. This hidden chasm stretches silently across Greenland, a subterranean monument to forces we have yet to understand, the mysterious meltwater rivers inside the ice. The first signs of flowing water within the ice startled researchers, revealing a hidden network that defied all expectations of Greenland's frozen interior. Instruments initially designed to measure ice thickness instead picked up subtle anomalies, faint echoes that suggested cavities filled with liquid moving beneath kilometers of solid ice. These flows appeared in places long considered static, untouched by melt or seasonal thaw, raising questions about how water could persist under immense pressure and near freezing temperatures. The realization that the ice sheet concealed entire rivers beneath its surface challenged long-held assumptions and introduced a profound sense of mystery. Invisible channels twist and turn beneath the surface, forming a subterranean web that guides meltwater across vast distances in near-complete darkness. Some pathways snake for dozens of kilometers before resurfacing at isolated outflow points, while others pool into ephemeral lakes trapped beneath the ice. The scale of this network is staggering, with multiple interconnected conduits operating simultaneously yet largely undetectable from above. Scientists compare the system to a secret circulatory system within the glacier, alive with motion yet entirely concealed, shaping the ice's movement in ways that remain mostly speculative. Pressure from thousands of meters of overlying ice creates conditions that allow these rivers to persist, their flow sustained by heat and friction in ways scientists cannot fully explain. As ice slides imperceptibly over bedrock, it generates warmth that prevents complete freezing, creating microchannels where water can continue to move. Laboratory simulations and field measurements have captured only fragments of this process, revealing a delicate balance between melting, freezing, and mechanical stress. Even small variations in temperature or ice thickness can alter the flow dramatically, leaving researchers puzzled about the stability and persistence of these systems. Mapping these elusive currents requires a combination of radar, seismic readings, and satellite measurements, each method offering only partial glimpses into the river's complex paths. Ice-penetrating radar reveals anomalies suggesting cavities, while seismic surveys detect the subtle vibrations of flowing water beneath. Satellite altimetry tracks changes in surface elevation that hint at subsurface drainage. Despite the sophistication of these tools, every method leaves gaps in understanding, producing maps that are part conjecture, part verified observation. Piecing these fragments together is akin to reconstructing a puzzle with most of the pieces hidden from sight. Evidence suggests some channels have existed for millennia, carved gradually by seasonal melt and refreezing, yet new formations continue to appear as the ice evolves. Ancient ice cores reveal patterns of meltwater entrapment, showing repeated cycles over thousands of years. Yet contemporary melting, driven by climate change, introduces new energy into the system, creating channels that were non-existent decades ago. This duality of enduring ancient rivers alongside transient, newly formed streams creates a dynamic and enigmatic environment, where each discovery raises more questions than it answers about the forces shaping Greenland's ice. The rivers subtly reshape the ice above, smoothing some sections, carving unexpected cavities in others, and influencing the ice sheet's movement in ways still difficult to quantify. In some areas, the water lubricates the base, accelerating the glacier's flow toward the ocean, while in others it freezes in place, creating bulges and pockets that distort surface measurements. These interactions are far from uniform, producing patterns that defy simple modelling and confound even experienced glaciologists. Each discovery underscores the complexity of the ice's interior, revealing a landscape of motion and change hidden from conventional observation. By analysing sediment and isotopic traces carried in the meltwater, scientists hope to reconstruct Greenland's ancient climate, although the full record remains tantalisingly out of reach. Minute particles embedded in water streams offer clues about past storms, volcanic eruptions, and seasonal temperature fluctuations. Isotopic ratios hint at the source and age of the water, helping researchers infer the ice's movement and melting history. Yet the full picture is incomplete, as many channels remain unexplored, leaving vast portions of the ice sheet's internal history encrypted within these liquid veins, waiting for interpretation. Small pockets of liquid water trapped along these rivers could harbour microbial life, preserved in isolation for thousands of years, hinting at unseen ecosystems hidden in the ice. Extreme cold, darkness, and high pressure have not necessarily prevented life from enduring. Microorganisms capable of surviving in subglacial lakes suggest that meltwater channels might serve as refuges. Sampling is rare and technically challenging, but every discovery of microbial life raises the possibility that these rivers are more than geological phenomena. They are habitats that have persisted unseen for centuries, offering insight into resilience and survival in extreme environments. Glaciologists debate how rapidly these meltwater networks evolve, with some arguing that sudden pulses of water reshape channels in hours, while others see evidence of slow, persistent flow. Seasonal thaw and meltwater surges can suddenly redirect currents, eroding ice and sediment along the way, whereas some rivers maintain stable paths for decades. The disagreements reflect both the difficulty of observation and the unpredictable nature of ice dynamics, leaving a spectrum of hypotheses in play. This uncertainty amplifies the mystery, as no single model can yet account for the scale, speed, and variability of the system. Modern warming may be altering the river's courses and intensity, suggesting that these hidden currents could play an unexpected role in ice sheet stability and sea level rise. Accelerated melting introduces larger volumes of water, changing pressure patterns and flow paths while potentially triggering collapse in vulnerable areas. The interaction between climate and subglacial hydrology is only beginning to be understood, but it has profound implications for predicting future ice behaviour. Even subtle shifts in these subterranean rivers may ripple outward, influencing Greenland's ice mass and global oceans in ways that remain largely speculative. Despite sophisticated measurements and decades of research, the full extent, behaviour and origin of these subterranean rivers remain a secret guarded by the ice itself. Every new observation leads to further questions about flow patterns, water sources, and interactions with bedrock and ice layers. The rivers continue to challenge expectations, demonstrating that Greenland's ice is not inert but alive with motion and unseen complexity. Each discovery amplifies curiosity as scientists confront an environment that resists full comprehension and conceals as much as it reveals. These subterranean currents carve paths through Greenland's frozen heart, carrying mysteries of water and time that have never been witnessed by human eyes. The strange movement of Greenland's zombie ice. Scientists first noticed patches of ice moving unpredictably, challenging centuries of assumptions about glacial rigidity. In regions previously thought inert, sudden shifts and surges seem to defy the rules governing frozen landscapes. Greenland's ice sheet, vast and unbroken in appearance, hides beneath its surface a network of forces and pressures that only recently have begun to reveal themselves. Researchers examining historical records realised that the phenomenon had been ongoing for decades, yet the mechanisms driving it remained obscure. The mystery is compounded by the fact that some areas advance slowly, almost imperceptibly, while others accelerate sporadically, creating a patchwork of motion that has no clear explanation. High-resolution satellite imagery reveals subtle shifts that suggest forces at play deep within the ice sheet. Through decades of observation, scientists have documented minor displacements that accumulate over time, altering surface contours and crevasse patterns. Infrared and radar imaging detect differences in ice density and internal layering that hint at channels of movement beneath. These observations indicate that the ice is not a monolithic mass, but a complex dynamic system, reacting to both internal and external stimuli. Even small changes in temperature or pressure at depth appear to ripple outward, producing shifts at the surface that are detectable only through precise instruments. Meltwater trapped beneath thick layers of ice seems to lubricate certain zones, producing movements that defy conventional explanations. During the summer months, surface melting percolates downward, forming pockets of water that reduce friction between ice and bedrock. In some cases, these meltwater networks coalesce into channels capable of rapidly accelerating localized ice flows. Scientists are still unsure how such hidden waterways interact with the immense weight of overlying ice or why similar formations elsewhere do not produce comparable effects. The presence of this water complicates predictions of ice sheet behavior, suggesting that Greenland's frozen expanse may conceal far more restless processes than previously thought. Long-term surveys indicate that some stretches of the ice creep at irregular intervals, as though obeying a hidden rhythm. Measurement stations installed across key sectors reveal sudden accelerations, followed by periods of near stagnation. Unlike typical glacial movement, which is gradual and predictable, these anomalies occur without apparent seasonal or climatic triggers. The irregularity challenges existing models, forcing scientists to consider unconventional explanations. Is the ice reacting to unseen subglacial currents? Or are there structural features within the bedrock guiding its motion? Each new survey only deepens the mystery, as the sheet appears to move with a life of its own. Researchers have proposed that thermal fluctuations or pressure pulses may trigger sudden slips, yet no theory fully accounts for the observed patterns. Ice viscosity changes with temperature, but Greenland's extreme cold should limit such effects. Similarly, while gravitational and tectonic forces contribute to glacial dynamics, they cannot explain the localized, erratic movements that have been recorded. Investigators have suggested that pockets of pressurized gas or trapped air may act like hydraulic pistons, releasing energy in ways that propel sections of ice forward. These hypotheses remain largely speculative, and no single mechanism has yet provided a complete explanation. Instruments embedded in the ice, from radar probes to GPS markers, have recorded tiny displacements that hint at a restless undercurrent. Over months and years, repeated measurements show cumulative motion that is measurable yet unpredictable. The patterns reveal that ice, though appearing solid and immutable, is in fact extraordinarily sensitive to forces beneath the surface. Even minute variations in basal conditions, temperature, pressure, or water flow, can propagate through the sheet and emerge kilometers away as visible shifts. Such findings have transformed scientific understanding of glacial dynamics, presenting Greenland's ice not as a static mass but as a complex, almost sentient system. The glacier stretches and bends in ways that appear almost intentional, reacting to unseen stresses beneath its frozen surface. Crevasses open and close, ridges shift subtly, and sections of ice accelerate in irregular pulses. These behaviours suggest that the ice is not passively conforming to gravity alone, but is actively responding to conditions buried within the bedrock and subglacial channels. Geophysicists have documented instances where neighbouring ice streams move independently yet in harmony, as though synchronised by a hidden network of forces. Each observation raises new questions about the energy transfers and structural mechanics at work deep below the surface. Certain ridges and troughs exhibit sudden accelerations, moving faster than the surrounding ice without any apparent trigger. These bursts of speed are brief, often lasting only hours or days, but they leave visible traces in crevasse patterns and surface deformation. The causes remain elusive, with researchers debating the role of meltwater surges, seismic events, or internal ice fractures. What makes these phenomena particularly puzzling is their spatial selectivity. Adjacent ice may remain static while isolated zones lurch forward. No consistent environmental or geological explanation has yet been confirmed, leaving the behaviour of these regions an enduring enigma. Subsurface channels, temperature variations, and pressure anomalies interact unpredictably, producing flows that continue to puzzle scientists. Studies of ice cores reveal layers of stress and movement recorded over centuries, but translating these patterns into predictive models has proven difficult. Even advanced computer simulations struggle to replicate the sporadic surges observed in the field. Each new measurement uncovers additional complexity, suggesting that Greenland's ice sheet harbours a network of hidden forces that defy simple categorization. The cumulative effect is an ice sheet that behaves with a degree of autonomy, shifting and reshaping itself in ways that remain only partially understood. These unusual movements may influence Greenland's ice sheet stability, altering meltwater drainage and the trajectory of glacial shifts in ways yet to be fully understood. If certain zones accelerate while others remain stationary, the internal stresses could trigger larger-scale collapses or reconfigurations over time. Understanding these dynamics is essential for predicting sea level rise, yet the sporadic and enigmatic nature of the ice's behaviour complicates forecasting. Scientists continue to monitor the sheet closely, employing every available method to capture the subtle rhythms and sudden motions that characterise this restless, frozen expanse. Observations over extended periods show that the ice behaves with a strange persistence, advancing and receding like a silent, uncharted force. Despite decades of study, the irregular and unpredictable surges persist, revealing a system more intricate than previously imagined. The ice reacts not only to temperature, meltwater, and pressure, but possibly to forces not yet fully detected or understood. Greenland's so-called zombie ice continues to defy expectations, its slow yet determined movements resisting any attempt at complete explanation. Within this frozen labyrinth, the ice moves with a subtle and deliberate patience that no one has yet explained. The forgotten Inuit stone structures of the far north. Even amid the vast, icy expanse of Greenland, where glaciers carve silent valleys and the wind whispers across frozen fjords, archaeologists have uncovered clusters of stone structures whose origins defy simple explanation. These formations, often circular or labyrinthine in layout, dot remote stretches of the northern coast, far from any contemporary settlements, and have perplexed researchers who struggle to determine why ancient Inuit communities went to such lengths to construct them. The stones themselves, arranged with apparent precision, suggest deliberate planning, yet their function, ceremonial, navigational, or otherwise, remains a subject of heated debate. Some sites are situated on elevated terrain overlooking ice flows, which raises questions about whether they were designed to mark territory, serve as vantage points, or communicate with distant communities through visual signals. Some formations consist of low, stacked walls forming semicircular shapes, while others appear as alignments pointing towards specific topographical features. The largest known sites, such as those near Thule, stretch over several hundred metres, implying significant effort over generations. Unlike typical hunting shelters or simple markers, these structures lack evidence of domestic activity. There are no hearths, discarded tools, or animal bones associated with daily life. Their isolation raises immediate questions. Why transport heavy stones across challenging terrain, often in areas buried under snow for much of the year, if they served no clear practical purpose? In several locations, smaller stone arrangements lie near larger complexes, suggesting a hierarchy of constructions that may have held social or ritual significance. Radiocarbon dating of nearby artifacts suggests that some structures may date back as far as 1,000 years, yet their construction methods defy straightforward categorization. Many stones are unusually uniform in size or carefully balanced, indicating knowledge of weight distribution and stability. Modern engineers have noted that several stone arrangements could withstand harsh Arctic storms without collapse for decades, a testament to Inuit ingenuity, though this alone does not reveal why they were built. Geologists also observe that the stones come from nearby outcrops, suggesting the builders were selective, hauling specific rocks rather than using readily available fragments. Evidence of deliberate shaping on certain stones further implies a level of craftsmanship that contradicts the structure's remote and utilitarian appearance. The locations themselves often seem chosen for reasons that elude explanation. Some sit atop bluffs overlooking fjords, offering panoramic views of ice-choked waters, while others occupy windswept plateaus far from hunting grounds. Researchers have speculated these sites may align with celestial events, including solstices or equinoxes, hinting at an early form of astronomical observation. Yet not all formations conform to this theory. Some clusters lie in valleys where horizon lines are obscured by mountains or drifting ice, undermining consistent astronomical interpretation. In a few cases, stone lines appear to trace the paths of glaciers, suggesting that builders may have been marking shifting ice or water routes, though the logic behind such markings remains speculative. Ethnographic records from early 20th century explorers provide tantalizing hints, but no concrete answers. Accounts from Danish and Inuit observers describe stone circles used for ritual or signalling purposes, but such narratives rarely specify locations or construction details, leaving modern researchers to piece together fragments of oral history with the surviving stones. The ephemeral nature of Arctic life means much knowledge was never documented, and the passage of centuries has left the meanings behind these structures largely inaccessible. Some oral histories even hint at spiritual significance tied to the landscape, describing certain stones as the dwelling places of ancestral spirits or guardians, yet these traditions cannot be verified through material evidence. Field studies have revealed patterns in construction that suggest more than mere randomness. Many stones are arranged in pairs, with gaps that might have allowed line-of-sight communication or facilitated the tracking of seasonal animal movements. Some structures contain small depressions or cavities, possibly for offerings or symbolic purposes, though archaeologists caution against overinterpretation. Despite detailed surveys and careful mapping, no single theory unifies all sites. Some may have served practical functions, while others were purely ceremonial, or perhaps these roles overlapped in ways no longer evident. Intriguingly, a few sites are oriented toward coastal fjords rather than inland hunting grounds, implying a connection to maritime activity or ritual observation of the sea. Environmental factors also complicate the picture. The shifting ice sheets and permafrost have altered the landscape over centuries, meaning some structures may now sit in positions very different from those originally intended. Stones buried under seasonal snowdrifts might have been exposed or hidden in cycles invisible to modern observers. Furthermore, erosion and frost heave have displaced or toppled many formations, obscuring their original layout and further frustrating attempts to understand their creators' intentions. In some instances, subtle traces of human pathways or dragging marks across bedrock hint at the immense effort required to move and place stones, emphasizing the importance of these constructions to the communities that built them. In recent years, researchers have applied advanced technology to these enigmatic sites. Ground-penetrating radar and satellite imaging have revealed subsurface anomalies beneath some stone clusters, including buried platforms or depressions that might indicate construction phases no longer visible on the surface. LiDAR mapping has allowed scientists to detect subtle geometric patterns, raising questions about whether these arrangements represent symbolic landscapes rather than purely functional structures. Yet even with these tools, interpreting the purpose of each formation remains speculative, limited by the absence of written records or contemporaneous explanation. In several surveys, LiDAR data revealed smaller, previously unnoticed stones surrounding larger circles, suggesting a complexity that had gone unrecorded for decades. Comparisons with other Arctic regions provide partial context, but introduce new mysteries. Similar stone arrangements exist in northern Canada and Alaska, built by different Inuit groups, yet the Greenland structures often display a scale and precision not seen elsewhere. Some researchers propose a shared cultural knowledge transmitted along ancient trade or migration routes, while others argue that local environmental pressures produce convergent construction techniques independently. Whatever the explanation, the Greenland formations remain distinct in their concentration and apparent intentionality. In contrast to other regions, Greenland's harsh climate and vast isolation make the persistence of such large stone complexes even more striking. Debates over these stone structures extend beyond archaeology into anthropology and cognitive science. Questions arise about the symbolic thinking of ancient Arctic peoples, their understanding of landscape and memory, and the role of ritual in survival-focused societies. Did these structures function as mnemonic devices for seasonal hunting, markers for spiritual journeys, or territorial claims visible across frozen plains? Evidence provides only fragments, and each discovery seems to generate more questions than answers, as if the landscape itself guards the reasoning behind these deliberate constructions. Researchers have also noted that some alignments subtly coincide with migratory paths of caribou and polar bears, though whether this was intentional remains uncertain. Field researchers often describe a sense of unease when surveying the sites in isolation, the silence of the Arctic amplifying the mystery. The stones stand as mute witnesses to lives lived in extreme conditions, their purpose obscured by time, ice, and cultural loss. Even when catalogued, measured, and photographed, they resist easy explanation, leaving scientists to acknowledge both the ingenuity and the unknowable aspects of the past. Many of the more remote structures are only accessible during brief summer windows, emphasizing the fragility of knowledge itself in a region dominated by impermanence and shifting ice. Somewhere amid the windswept bluffs and ice-choked valleys of northern Greenland, the true purpose of these ancient stone structures waits, hidden beneath centuries of snow and silence. The unexplained methane plumes along Greenland's coast. Methane rises in irregular columns along Greenland's northern coast, moving in ways that defy expectation and hint at hidden processes beneath the waves. Observations from decades of oceanographic study reveal that these emissions are neither uniform nor predictable, appearing in some locations and vanishing in others, sometimes lingering for hours without any apparent trigger. The plume's existence was first noted during surveys that tracked unusual gas concentrations in water samples, prompting further investigation into what could release such volumes from the seafloor. The scale is striking. Individual plumes can stretch hundreds of meters in height, while clusters may cover entire subsea ridges. Despite advanced measurement techniques, the mechanisms behind these emissions remain unresolved, leaving the phenomenon one of Greenland's most perplexing mysteries. Concentrations fluctuate across the seafloor, sometimes intensifying over days before dissipating almost entirely, a pattern that defies conventional physical expectations. Researchers using chemical sensors have documented spikes in methane levels that appear unconnected to tides, storms, or seasonal cycles. These irregularities suggest that the ocean floor is far more dynamic than previously thought, with pockets of trapped gas potentially building pressure over centuries before releasing. Instruments deployed on remotely operated vehicles detect microbubbles escaping in sheets or columns, yet in other areas, the gas seems trapped in sediment layers, invisible to any direct measurement. This unpredictable behavior complicates attempts to model the plume's formation or anticipate their impact on surrounding ecosystems. Subtle ridges and depressions on the seabed appear to channel gas along invisible pathways, as though the underwater terrain itself is shaping the phenomenon. Bathymetric surveys have revealed depressions that seem to align with the locations of recurring plumes, suggesting that small changes in topography may concentrate or direct emissions. The formations of the seafloor vary from gentle slopes to jagged outcrops, and in each case the methane behaves differently, rising in narrow, concentrated streams in some areas while spreading laterally in others. Even minor sediment shifts can alter the flow, emphasizing the sensitivity of this system and hinting at mechanisms that scientists are only beginning to hypothesize. Frozen methane hydrates and minor tectonic activity have been proposed as sources, yet neither fully accounts for the size, frequency, and behavior of the plumes. Hydrate destabilization can release trapped methane when warmed, but observed releases occur in conditions colder than expected for melting, raising questions about additional triggers. Similarly, subtle tectonic movement may open fissures, yet these events do not explain the sustained, cyclical, or clustered patterns that persist over years. Some studies suggest that a combination of thermal, geological, and oceanic factors may be at work, though no single explanation has yet passed rigorous testing or been observed directly in real time. Water chemistry around the emissions changes measurably, altering oxygen levels and influencing microscopic life in ways that challenge conventional Arctic models. Dissolved gases from the plumes modify local carbon and nutrient balances, which can affect plankton populations and alter the composition of microbial communities. These effects extend further than the immediate site, as currents transport methane-laden waters through fjords and into open ocean channels. Even minor concentrations can influence chemical equilibrium, demonstrating that the plumes are not merely isolated phenomena but active participants in Greenland's marine environment, carrying consequences that remain only partially understood. Some plumes gradually expand over hours, while others form tight, concentrated streams, producing an unpredictable rhythm that continues to puzzle researchers. Time-lapse monitoring of individual sites reveals that the release rates can accelerate or slow without warning, with no obvious connection to surface conditions, temperature or depth. This irregularity complicates sampling, forcing scientists to design increasingly sophisticated monitoring equipment capable of recording rapid changes. In several cases, plumes detected one day are gone the next, while previously dormant locations suddenly activate, illustrating that the system is not static and suggesting that unseen factors, perhaps chemical or structural, govern their activity. Repeated measurements over decades confirm the phenomenon's persistence, though the extreme isolation of Greenland's coast means much remains unobserved. Early expeditions noted methane anomalies in seawater samples, yet the lack of continuous tracking left their temporal behaviour largely undocumented. Modern satellite imagery and remote sensing provide improved spatial coverage, but fine-scale temporal patterns remain elusive. The episodic nature of emissions, combined with the logistical challenges of Arctic research, means that even extensive data sets offer only snapshots of the phenomenon, leaving significant gaps that prevent definitive conclusions. Certain emissions rise vertically while others spread laterally, revealing behaviours that resist simple physical interpretation. Some narrow columns maintain their shape for hundreds of metres, while diffuse sheets of gas meander along the seabed before reaching the surface. Laboratory simulations struggle to replicate these conditions, as the interplay of pressure, sediment composition, and gas concentration produces results that differ depending on minor variables. This complexity underscores the uniqueness of Greenland's methane plumes, and highlights why scientists are unable to provide a comprehensive explanation despite decades of careful study. Seasonal melting and sediment shifts appear connected to certain emissions, though researchers cannot establish a clear causal relationship. Thawing permafrost and retreating glaciers may loosen trapped gas or alter pressure conditions, yet not all plumes coincide with periods of melt, and some appear in frozen conditions that should theoretically prevent release. Subtle changes in seabed sediments, including slumping or displacement from undercurrents, may trigger emissions, yet these observations are inconsistent and vary from year to year. The partial correlations tantalize researchers, suggesting that the Arctic is both a reactive and enigmatic system, one that resists simplistic explanations. Gradual seepage and sudden destabilization have both been suggested, but each hypothesis leaves gaps in understanding that deepen the mystery. Models of slow, continuous release fail to account for concentrated emissions observed in certain areas, while catastrophic destabilization scenarios cannot explain small, repeated plumes. Researchers acknowledge that multiple mechanisms may be at work simultaneously, interacting in complex and subtle ways that are invisible at the surface. The tension between measurable patterns and unobservable causes reinforces the sense that the methane plumes are a riddle embedded within a system of immense scale and complexity. The plumes continue to behave in ways that are tangible, measurable, and yet fundamentally elusive, defying full comprehension even in modern study. Each observation raises more questions than answers, and every new instrument deployed captures only a fraction of the dynamic reality. The gas moves according to invisible currents and forces, leaving a trail of evidence that points to activity both ancient and ongoing. As researchers catalogue the emissions, map their extent, and measure their impact, the underlying processes remain frustratingly just out of reach, a reminder of the mysteries still held by Greenland's coastal waters. Invisible currents carry the gas onward, leaving the question of its origin lingering like a riddle without an answer. The enigmatic Petermann glacier fractures. Deep fissures have begun to etch themselves across the ice, splitting the glacier in ways that challenge the predictions of current models. Petermann Glacier, one of Greenland's largest, stretches over hundreds of kilometres, yet its fractures form seemingly at random, cutting through layers that should provide stability. Researchers monitoring the ice have noted that some cracks widen slowly over weeks, while others expand rapidly, producing ice islands that break away with startling force. These fractures are not minor. They carve paths through kilometers of solid ice, and despite decades of study, scientists still cannot fully explain the precise mechanisms triggering their sudden appearance. Recent measurements show fractures extending for kilometers, yet the rate and direction of their propagation often confound expectations. Satellite imagery captured over multiple seasons demonstrates that some cracks grow in straight linear paths, while others twist or branch unpredictably. The complexity is compounded by the glacier's flow, which moves ice toward the sea at varying speeds. While modelling can predict general movement, the exact timing and trajectory of individual fractures remain uncertain, leaving even the most advanced forecasting tools inadequate to fully anticipate calving events. The glacier's immense thickness and internal layering suggest pressures that should produce slow shifts, but sudden movements frequently defy these assumptions. Petermann Glacier can reach thicknesses of over 600 metres, and the weight of this ice creates internal stress that might be expected to dissipate gradually. Yet fracture propagation does not always follow these patterns. Some cracks form abruptly across otherwise uniform sections, slicing through hundreds of metres of ice in mere days. The irregularity of these formations continues to puzzle glaciologists who track stress accumulation and ice flow, suggesting that additional hidden forces may influence the process. Advanced radar and satellite imaging reveal anomalies beneath the surface, indicating zones of stress and weakness whose origins remain unexplained. Ice-penetrating radar has detected cavities and channels inside the glacier, and subtle shifts in the ice's density appear to correlate with emerging fissures. These anomalies suggest that fractures may be influenced by conditions deep within the ice sheet, including trapped meltwater or uneven layering, yet no single factor has been shown to trigger the events consistently. Each discovery seems to illuminate one part of the glacier's behaviour while leaving other questions unresolved, reinforcing the sense of an intricate and largely hidden system. Variations in temperature and tidal forces coincide with some cracks, though many occur independently of these environmental factors. During warmer months, surface meltwater can seep into existing crevices, potentially accelerating fracture growth, yet similar fissures have been observed in frigid conditions with little surface melting. Tides can flex the glacier's terminus, but this influence does not explain fractures farther inland. These inconsistencies highlight the limitations of existing models and demonstrate that the glacier operates under forces that are only partially understood, blending predictable ice physics with events that seem almost arbitrary. Gigantic ice islands detach with startling force, sometimes moving unpredictably before settling, a dramatic consequence of fractures that scientists still cannot fully anticipate. Some calving events produce icebergs over a kilometre long and hundreds of metres thick, displacing massive volumes of water and sending waves through fjords. Tracking these ice islands is complicated, as they can drift for weeks before stabilising, and small variances in fracture alignment can drastically affect their movement. Even with modern monitoring techniques, each calving event feels partially unscripted, a reminder that the glacier maintains its own rhythm beyond human understanding. Historical records document repeated calving events, but no consistent pattern explains the timing or location of each new fissure. Satellite images dating back to the 1970s show that Petermann Glacier has repeatedly generated fractures in similar zones, yet the intervals and sizes of these fractures vary widely. Reports from early expeditions describe ice islands breaking away in ways that astonished observers, emphasizing that this is not a recent phenomenon but a long-standing characteristic of the glacier's behavior. Despite accumulating decades of observation, the underlying triggers remain elusive, leaving scientists with detailed records but few answers. Certain fractures branch unexpectedly or accelerate along unexpected trajectories, displaying behaviors that defy conventional understanding of glacial physics. Some cracks begin slowly, then suddenly veer into new directions or widen at rates far exceeding model predictions. These patterns suggest that forces within the glacier are unevenly distributed, potentially influenced by hidden channels of meltwater or internal ice deformation. Attempts to simulate such behaviours in laboratory conditions or computer models have been partially successful, but no experiment has captured the full complexity of the fracture dynamics observed in situ. Theories range from internal ice stress to meltwater infiltration or subglacial activity, yet none completely accounts for the glacier's enigmatic behaviour. Stress accumulation due to ice flow can explain some fracture initiation, but it fails to address the sudden accelerations or unusual branching observed. Meltwater infiltration may lubricate internal cracks, yet fractures often appear where minimal meltwater exists. Subglacial seismic activity could influence fracture growth, but measurements of tectonic motion near Petermann are minimal and inconsistent. Each proposed mechanism explains fragments of the phenomenon while leaving large gaps, reinforcing the glacier's reputation as one of Greenland's enduring mysteries. Observers tracking the glacier describe a quiet tension, as if the ice conceals forces that are both massive and invisible, revealing themselves only intermittently. Scientists monitoring fracture progression via remote sensing report the slow, almost imperceptible prelude to major calving, a series of subtle shifts that can herald a dramatic break. There is an unease in witnessing these events unfold, as the glacier appears to harbour agency, responding in ways that resist prediction or control. Even with high-resolution imagery and continuous monitoring, the fractures advance in ways that are tangible yet largely incomprehensible. The glacier's surface appears static at first glance, yet beneath that apparent calm the fractures advance, leaving scientists struggling to interpret their underlying mechanics. Ice sheets are not silent witnesses, their movement, stress and fracture dynamics are constant, though often invisible. The combination of slow flow, hidden channels, and sudden fracture propagation creates a system that is difficult to quantify, let alone fully understand. For those observing, the Petermann Glacier is a living paradox, immense, enduring, and yet capable of sudden transformation that challenges every assumption about glacial behaviour. The cracks stretch across the ice like cryptic messages, each fracture a question the glacier has written but refuses to answer. The buried Viking trade routes across the ice. Scattered remnants hint at journeys that once stretched across Greenland's interior, yet the routes that carried them remain largely invisible under centuries of ice and snow. Archaeologists have long noted traces of Norse activity beyond the known coastal settlements, and while some items have been recovered, the paths connecting them continue to elude precise identification. Subtle depressions in the ice and occasional artifacts suggest repeated movement, as if the Vikings traversed vast frozen expanses along trails now obscured by glaciers. Each discovery deepens the mystery, raising more questions about the scope and purpose of inland travel in an environment so unforgiving that survival itself was a daily challenge. Rusted tools, fragments of iron, and traces of animal hides emerge sporadically, suggesting repeated passage far beyond the coastal settlements long associated with Norse activity. Excavations have revealed scattered remnants that could only have been transported deliberately, hinting at trade or communication routes across the interior. The irregular distribution of these artifacts raises questions about how frequently Vikings crossed the ice and what influenced their choice of paths. Even in places where materials are found, the surrounding terrain often shows no clear evidence of permanent habitation, implying movement rather than settlement. Layers of permafrost and glacial ice have preserved artifacts for centuries, concealing evidence even as they guard it from decay. Organic materials, normally lost to time in other environments, survive remarkably well here, yet their isolation under ice complicates verification. Some items lie several meters below the surface, trapped in sediments that have shifted over centuries, making excavation slow and painstaking. The preservation is a double-edged sword. It offers a time capsule into Viking activity while simultaneously keeping the full picture just out of reach. A mystery frozen as effectively as the artifacts themselves. Ground-penetrating radar and aerial surveys reveal subtle linear alignments, faint impressions that may mark trails or paths worn by repeated travel. These signals often appear as narrow streaks or low ridges that cut across the ice sheet, suggesting intentional movement rather than natural formation. Some patterns extend for kilometers, while others terminate abruptly, leaving researchers to speculate on whether they represent seasonal paths, temporary routes, or traces of lost settlements. Confirming their purpose is challenging, as many indicators are shallow or faint, and ice movements over centuries have altered their original appearance. Geographic features and treacherous terrain hint at the challenges faced by those who cross the interior, forcing routes to adapt to mountains, rivers, and ice flows. The Vikings would have had to navigate areas where snowdrifts, crevasses, and hidden streams presented constant hazards, relying on knowledge of seasonal conditions and environmental cues. Narrow valleys or frozen rivers may have served as natural guides, yet even these highways were precarious. The combination of extreme cold, unpredictable weather, and scarce resources meant that any inland expedition carried immense risk, raising questions about why the Vikings repeatedly undertook such journeys. The objects carried along these routes, ivory, iron and furs, leave tantalizing traces, pointing to a trade network far more extensive than records suggest. Ivory from walrus tusks, iron tools and other goods moved from the coast into the interior reveal a level of planning and coordination previously underestimated. Such items, preserved by ice or recovered from sediment layers, suggest that movement across Greenland was not incidental but intentional, connected to commerce, communication, or perhaps seasonal hunting. Each recovered artifact serves as a silent witness to journeys that were arduous, carefully orchestrated, and largely invisible to modern eyes. Uneven distribution of settlements and stray artifacts raises questions about why some inland locations were repeatedly visited, while others were bypassed entirely. Patterns of artifact clusters hint at favoured paths or staging areas, yet no single explanation accounts for why certain zones were chosen. Perhaps terrain features, proximity to resources, or environmental conditions influence selection, but the evidence is incomplete. The irregularity adds an air of mystery. The routes appear purposeful but leave gaps too wide for straightforward reconstruction, as if parts of the network have been lost beneath centuries of ice and snow. Historical records confirm Norse colonies on Greenland's coasts, but evidence of inland crossings remains scarce, leaving a profound gap in understanding their reach. Written accounts, sagas and archaeological reports document settlements in the southwest and along fjords, yet the interior appears largely uncharted in historical sources. Despite these limitations, the scattered physical evidence suggests that Vikings may have ventured far from familiar territories, relying on oral knowledge, survival skills, and the unyielding observation of the environment. The contrast between written history and physical traces underscores how much of Greenland's inland past remains hidden from human record. Theories abound, from temporary encampments along pack routes to seasonal migrations across icefields, yet no single explanation fully accounts for the patterns that emerge. Some archaeologists propose that interior crossings facilitated trade between coastal settlements, while others suggest hunting or exploration as primary motives. Seasonal variation may have influenced timing, with ice and snow conditions dictating when travel was feasible. Still, the fragmentary evidence leaves all these possibilities open, maintaining the suspense of a system only partially reconstructed, with many routes and practices lost to time. Shifting ice sheets over centuries have hidden and revealed passages in turn, complicating the task of reconstructing routes that may no longer be visible. A glacial advance can bury paths, while retreat may expose previously invisible traces. Archaeologists attempting to map these routes must account for movement over centuries, meaning that current observations may not perfectly align with original travel corridors. The dynamic nature of the ice adds layers of uncertainty, ensuring that any reconstruction is provisional, tentative, and prone to revision as new findings emerge, or glaciers shift once more. Traces of human endurance persist in subtle ways, suggesting journeys across frozen expanses that challenged both survival and navigation in equal measure. Even fragmentary paths, isolated tools, and scattered settlement remains tell a story of adaptability, skill, and persistence. The Vikings who traversed Greenland's interior confronted extreme conditions with ingenuity, leaving hints of their presence in patterns too faint to interpret fully. Each discovery, no matter how small, raises as many questions as it answers, reinforcing the sense that the interior of Greenland contains chapters of history still inaccessible to modern understanding. Encased in the ice's silent depths, the paths they carved endure like whispers of a history that refuses to be fully uncovered. The curious case of Greenland's ice tsunamis. Towering waves have been recorded surging through fjords after massive sections of ice suddenly collapse into the water, a phenomenon scientists still struggle to explain. Witnesses have described water rising with alarming speed, swallowing small icebergs and crashing against cliff faces with tremendous force. These events unfold unpredictably, sometimes triggered by large calving episodes, other times with no obvious precursor. Each occurrence challenges conventional understanding of glacial dynamics and tidal interactions, leaving experts to puzzle over the factors that might align to create such enormous sudden waves. The mystery endures, as if the fjords themselves hold secrets too vast to measure fully. Even the surrounding cliffs, with their jagged edges and frozen walls, seem to amplify the sound and power of each impact, echoing long after the wave has passed. Measurements indicate that some waves can reach tens of meters in height, spreading rapidly across narrow channels and striking with little warning. Instruments installed in key fjords track water displacement, noting peaks that often exceed expectations based on ice mass alone. Flow speeds can surpass those of ordinary tidal surges, carrying debris and fragments of ice for kilometers. In certain locations, wave propagation accelerates as channels narrow, amplifying the force and intensity. These observations are consistent yet unpredictable, suggesting a combination of glacial activity, topography, and fluid dynamics that science has yet to fully reconcile. The persistent unpredictability contributes to a growing sense of caution among crews navigating nearby waters. The mechanics of glacier carving suggest a slow release of pressure, yet the sheer force and speed of these ice-driven tsunamis often defy such expectations. Large ice blocks, sometimes hundreds of meters wide, dislodge with startling suddenness, displacing water far more violently than anticipated. Scientists have modelled wave formation based on volume and height, but the real-world observations often surpass theoretical predictions. Some waves appear to surge without a corresponding large carving event, hinting at hidden dynamics beneath the glacier's surface. The contrast between prediction and observation fuels both curiosity and caution in the study of these events. Additional measurements indicate that even minor fractures in the glacier's face can amplify vibrations throughout the ice, potentially contributing to sudden, larger-than-expected surges. Remote sensing and tide gauges track water displacement with increasing precision, yet the exact triggers and timing of each event remain elusive. Satellites record glacier movements, while high-precision instruments measure wave velocity and height, but anomalies persist. The timing between carving and the resulting wave varies widely, sometimes occurring within minutes, sometimes delayed by hours. Researchers continue to refine models, yet no method consistently predicts which glacier section will collapse next or the exact magnitude of the ensuing surge. Each event reminds them that the forces at play are not entirely understood, despite advanced observation tools. In some fjords, waves have reflected against incoming currents, creating rare interference patterns that further complicate analysis. Factors such as water depth, ice geometry, and accumulated meltwater appear to influence wave formation, though no single element accounts for every observed surge. Fjord width and shape can amplify or dampen waves, while submerged ice or sediment changes the flow unexpectedly. Meltwater channels within the glacier may weaken the base, triggering a sudden collapse, yet in some cases, massive waves occur where no internal water pathways are evident. Temperature fluctuations, seasonal ice thinning, and tidal cycles interact in ways that are difficult to quantify, creating a complex system that resists straightforward explanation. Researchers speculate that unseen cavities or fissures beneath the glacier might occasionally release pressure suddenly, further adding to unpredictability. These sudden waves can uproot smaller icebergs, shift sediments on the fjord floor, and send echoes of destruction that ripple far beyond the point of impact. Observers have documented overturned ice flows and submerged boulders carried long distances, as well as temporary disruption to marine habitats. Even minor collapses can generate surges that propagate across the fjord, affecting distant shores. The physical power of these ice tsunamis is evident in both the immediate destruction and the lasting changes to underwater terrain. Yet the factors determining which events produce extreme effects remain uncertain. In some cases, the waves have temporarily altered the salinity and temperature layers within the fjords, affecting marine life in ways still being studied. Historical accounts and local observations describe unusual surges of water, sometimes attributed to weather or seismic activity, but these explanations rarely fit the recorded evidence. Indigenous Greenlandic communities have noted abrupt waves in fjords for generations, describing sudden flooding and unusual sounds echoing across glaciers. Early explorers similarly reported unexpected waves, often attributing them to storms or ice shifts. Modern investigation has revealed that some of these historic reports likely corresponded to ice tsunami events, reinforcing the idea that the phenomenon is long-standing yet poorly understood. Certain anecdotal reports describe waves reaching settlements previously thought to be safe, hinting at the hidden force and reach of these events. Some ice tsunamis occur without significant calving, while others surpass predicted heights, revealing inconsistencies that continue to confound researchers. Cases where minor glacier movements produce outsized waves challenge assumptions about volume to impact ratios. Conversely, enormous calving events occasionally generate only modest surges, suggesting additional variables are at play. The irregularity frustrates attempts at modelling and forecasting, leaving even experienced glaciologists unsure when or where the next destructive wave might appear. These inconsistencies form the core of the ongoing mystery, reinforcing the notion that each fjord may behave differently depending on hidden underwater topography. Hypotheses range from subaqueous landslides to rapid glacier sliding, yet no single theory fully explains the combination of force, frequency, and unpredictability seen in these events. Some scientists propose that destabilized sediment beneath the glacier could suddenly shift, pushing massive amounts of water. Others suggest that hidden water pockets, pressurized by melting ice, might act as triggers. Seismic activity or minor quakes have been considered, but they cannot account for every observed surge. The interplay of these factors remains speculative, and no single explanation satisfies all observations, maintaining the suspense that surrounds Greenland's fjords. Occasional anomalies suggest that combinations of these mechanisms might occur simultaneously, producing waves of entirely unexpected magnitude. Those stationed along the fjords describe the roar of collapsing ice, the abrupt surge of water, and the fleeting instant when serene channels explode into torrents of raw power. Even with safety precautions, witnessing an ice tsunami evokes a sense of awe and vulnerability, as calm waters are transformed in moments. Sensors, cameras, and direct observation often capture only fragments of the event, leaving gaps in understanding that complicate analysis. The human experience of these tsunamis underscores their unpredictability, emphasizing the gulf between measurement and comprehension. The sound itself, reverberating across cliffs and frozen walls, seems to announce the power of forces beyond human control. Each successive event underscores the uncertainty that surrounds this phenomenon, leaving researchers with fragments of understanding rather than complete answers. Patterns emerge, then vanish, and theories are tested against reality, only to encounter new anomalies. The recurring inability to fully anticipate the wave's behaviour highlights the limits of current knowledge, as natural forces continue to operate with a degree of autonomy beyond human prediction. Even the most comprehensive models offer only glimpses of what may occur next, reminding observers that the fjords retain an authority all their own. Even after extensive monitoring, the waves surge with a mind of their own, leaving questions in their wake that refuse to settle. The disappearing Arctic ice caves. At the edges of Greenland's glaciers, delicate ice caverns emerge and vanish with startling speed, a phenomenon that continues to baffle scientists. These fleeting structures sometimes appear as shimmering tunnels beneath overhanging ice cliffs, while other times they stretch across frozen surfaces, hollowed from meltwater channels. Explorers and researchers have reported discovering intricate formations that seem to exist only for hours, leaving only faint traces of their presence after collapsing. Their sudden disappearance complicates efforts to study them systematically, and each transient cavern raises questions about the underlying forces shaping Greenland's glacial landscape. The impermanence of these caves seems almost deliberate, as if the ice is hiding its secrets in plain sight. These formations are carved by meltwater streams, subtle shifts within the ice, and seasonal temperature fluctuations that shape intricate tunnels and chambers. Water seeping through cracks in the glacier slowly melts internal ice, enlarging cavities that can grow into rooms large enough to walk through. Temperature variations between day and night create cycles of expansion and contraction, fracturing walls and ceilings. Even minor variations in sunlight can accelerate melting in some areas, while others remain stable for weeks. Scientists studying these processes note that the interaction between flowing water and moving ice creates geometries that often defy expectations, producing patterns and passages that appear almost architectural in their symmetry. Tracking the caves is a formidable task, as each structure may persist for mere days, collapsing before observers can fully document its dimensions or patterns. Field teams often arrive to find a cavern completely gone, leaving only smooth ice floors or scattered debris where walls once stood. The rapid changes make it difficult to map caves accurately, and repeated visits sometimes yield entirely different structures in the same location. Remote access is often the only option, using aerial imagery to record formations that may no longer exist by the time teams reach the glacier. The transient nature of the caves emphasizes both their beauty and the challenge of understanding a landscape in constant flux. Modern monitoring techniques, including drones and satellite imagery, capture fleeting glimpses of the caves, revealing glimpses of structures that seem almost too perfect to be natural. High-resolution photographs show arched ceilings, twisting corridors, and icy chambers that reflect light in prismatic patterns. Thermal imaging sometimes exposes hidden streams feeding the caves, revealing networks invisible to the naked eye. Yet even with sophisticated technology, entire passages vanish between observation periods, leaving gaps in the data and tantalizing hints at complexity that remains unresolved. Each new image captures a moment in time that may never occur, underscoring the ephemeral nature of these ice formations. Internal stress within glaciers and the constant movement of ice sheets contribute to sudden collapses, rendering some caves visible only in photographs after they have already disappeared. The pressure of overlying ice can fracture ceilings or walls without warning, sending shards tumbling into water-filled chambers below. Seasonal shifts cause expansions and contractions that loosen the structure, often creating instability in previously solid passages. Scientists have documented instances where caves appear robust one morning and are gone by evening, leaving a flat, featureless ice surface in their place. Such unpredictability makes it nearly impossible to forecast which formation will endure and which will vanish in an instant. The caves subtly influence meltwater channels and glacier flow, with each formation briefly redirecting water, ice fragments, and sediments in ways that challenge predictions. Streams redirected through caverns can carve deeper channels beneath the glacier, altering flow rates and affecting surrounding ice structures. Sediment trapped in meltwater sometimes accumulates in small chambers, later deposited elsewhere when the cavern collapses. Even minor changes in water volume can influence nearby crevasses and ice ridges, creating subtle feedback loops. Researchers recognize that while the caves may last only briefly, their presence can leave a measurable mark on the glacial landscape, a hidden trace of movement and transformation. Records from Greenlandic communities and early explorers describe tunnels of ice appearing unexpectedly, hinting that this ephemeral phenomenon has long intrigued humans. Oral histories speak of passages that formed and vanished, sometimes revealing hidden waterways or unusual acoustic effects within the ice. Early 20th century explorers noted caverns large enough to shelter equipment or provide temporary refuge. Yet by the time subsequent expeditions returned, these structures had vanished. These recurring reports suggest that the formation and disappearance of ice caves is a long-standing natural occurrence, one that continues to elude consistent scientific explanation despite modern instrumentation. Some caves defy expectation entirely, forming in areas thought too unstable or shallow, while others extend far deeper into the glacier than models would suggest. Researchers have encountered caverns beneath thin ice layers that should have been incapable of supporting such passages. Others find massive chambers carved far into the interior, with ceilings high enough to walk upright for dozens of meters. These anomalies challenge assumptions about ice density, melting patterns, and the internal hydrology of glaciers. The unpredictability and variance in size, shape, and location intensify the sense that the caves operate according to rules that science has not yet uncovered. Scientists have proposed explanations ranging from concentrated internal melting to hidden water pockets, yet no theory fully accounts for the timing, size, and sudden disappearance of these caves. Some models emphasize the influence of underground meltwater networks, while others consider glacial pressure and seasonal temperature swings. Yet no combination of these variables reliably predicts when a cave will appear or collapse. Even repeated observations of the same glacier often yield contradictory results, suggesting that unknown factors may govern the lifespan and structure of each formation. This persistent uncertainty keeps the phenomenon at the frontier of glaciological research. Researchers navigating icy corridors describe the eerie silence of the caves, punctuated by distant cracking and the occasional collapse that signals the impermanence of the formations. the quiet within a cavern can be profound, only interrupted by the sound of dripping water or shifting ice. The faint glow from translucent walls creates shadows that bend and shimmer as passages twist. Yet, in an instant, a chamber may collapse entirely, leaving a hollow shell or exposing new channels that did not exist moments before. These first-hand experiences reinforce the sense of unpredictability and the delicate, transient nature of the ice caves. Every newly formed cavern emphasizes the fleeting nature of these structures, leaving fragments of understanding and unanswered questions about their patterns and lifespans. Repeated observation often yields incomplete records, as photographs and measurements capture only a moment before the ice rearranges itself. Researchers can document formation processes, yet the disappearance of caves often occurs without warning or clear cause. Each event highlights the challenge of studying natural phenomena that exist on such brief, dynamic timescales, where the landscape itself seems to evade full comprehension. Each vanished ice cave leaves behind only hollow corridors and the unsettling sense that the glacier holds secrets we may never witness again. The strange magnetic anomalies beneath Greenland. Strange readings from Greenland's interior have left scientists puzzled, revealing magnetic patterns that seem to defy conventional understanding. Across the island, instruments register fields far stronger in certain zones than expected, while neighbouring regions show surprisingly weak intensity. These anomalies are irregular, often forming shapes and streaks that appear almost deliberate in their complexity, yet no known natural mechanism accounts for the precise configuration. Despite decades of research and increasingly sophisticated technology, the patterns continue to challenge geophysicists, creating a sense that Greenland's icy shell conceals forces that remain just beyond human comprehension. The isolation of these sites compounds the mystery, with the extreme cold and persistent winds limiting both access and the duration of fieldwork. Satellite data first highlighted irregular patches of magnetic intensity scattered across the ice with no obvious geological explanation. Surveys revealed elongated streaks running parallel in some areas, while in others, clusters of unusual strength form islands of intense magnetism. The sheer scale of these anomalies, spanning tens of kilometers in some cases, contrasts sharply with the lack of corresponding surface features. Glaciologists and geologists alike are confounded, as the ice itself does not indicate why these magnetic fluctuations appear where they do, or why some zones remain stubbornly constant while others change unpredictably. The precision required to capture these subtle variations adds to the challenge, as minor calibration errors in satellites can obscure small but critical details. Instrument teams in the field report fluctuations that cannot be replicated, even under controlled conditions, making measurements notoriously unreliable. Magnetometers carried across the same coordinates on different days often yield results that vary dramatically, sometimes by several hundred nanoteslas. Small variations in temperature, atmospheric pressure, or electronic interference seem insufficient to explain the changes. These inconsistencies complicate efforts to map Greenland's magnetic field with precision, leaving gaps in understanding and emphasizing the island's role as a laboratory of invisible phenomena. Field scientists often work in extreme isolation, navigating across ice that stretches uninterrupted for miles, all while balancing the technical demands of complex instruments in sub-zero temperatures. The ancient rock formations of Greenland provide only partial clues, as some strong magnetic signatures align with no known mineral deposits. Large swaths of Precambrian gneiss and granite dominate the subsurface, naturally producing some magnetic activity, yet many readings correspond to areas where no iron-rich rocks are expected. This mismatch hints at subsurface structures or compositions that have yet to be identified. The challenge is magnified by the thickness of the ice, which isolates researchers from direct observation and makes it difficult to confirm the geological sources of the anomalies. Some teams speculate that deep crustal movements or even remnants of ancient magma chambers may contribute to the unexpected intensity of the magnetic fields. Swaths of intensified magnetism twist and curve unpredictably, forming intricate patterns that challenge models of Greenland's subsurface structure. Lines of high intensity sometimes intersect with weak zones, creating configurations that resemble rivers or networks but do not correspond to any known geological feature. In some areas, magnetic strength rises and falls abruptly over short distances, as though the ice conceals chambers of unseen magnetized rock. Scientists remain unsure whether these patterns result from ancient tectonic shifts, localized mineralization, or some unknown geophysical process entirely. The dynamic nature of the ice and bedrock adds further uncertainty, as even minor shifts in glacier movement can subtly influence the readings. Advanced tools such as aeromagnetic sensors and ground-penetrating radar sometimes reveal fleeting anomalies that vanish by the next survey, deepening the enigma. Aircraft-mounted magnetometers provide detailed snapshots, but repeated passes often fail to replicate the same data points. Ground-penetrating radar occasionally detects subsurface features that appear magnetic, yet these structures may shift, dissolve, or vanish in subsequent scans. This inconsistency forces researchers to rely on composite datasets and statistical modelling, yet even sophisticated simulations cannot predict all observed anomalies, leaving the phenomenon partially unexplained. The layering of ice, sediment, and rock below adds complexity that challenges even the most refined analytical models. Several hypotheses have emerged, including concentrated mineral veins and ancient tectonic features, yet none explain the anomalies in their entirety. Some researchers suggest pockets of magnetite or other iron-bearing minerals may lie hidden beneath the ice, while others speculate that frozen magma or previously unknown volcanic structures could contribute. Tectonic stresses may realign magnetic domains in ways that create transient hotspots, yet these mechanisms fail to account for the rapid shifts observed in certain areas. The combination of scale, intensity, and unpredictability continues to elude comprehensive explanation, leaving the island's magnetic map riddled with gaps that ignite both curiosity and frustration. Compasses and other sensitive instruments occasionally register subtle deviations in specific areas, demonstrating that the anomalies have tangible effects. Field teams navigating Greenland's interior have noted that compass needles may swing erratically in localized zones, complicating mapping and navigation. Even electronic survey equipment can experience brief calibration errors when entering regions of unusually high magnetic flux. These disruptions, while minor, provide a physical manifestation of the anomaly's presence, reinforcing the notion that the magnetic forces are not just theoretical, but actively influence the environment above the ice. For explorers relying on precise instruments, even these small anomalies can create disorienting challenges in an already inhospitable environment. Globally, no other magnetic regions exhibit the same intensity and unpredictability, leaving Greenland uniquely perplexing to geophysicists. While areas of unusual magnetism exist in Siberia, Canada, and southern Africa, the combination of rapid variation, concentrated intensity, and location beneath thick ice sheets is unparalleled. Greenland's anomalies remain enigmatic not only because of their strength, but also because their patterns challenge assumptions about crustal magnetism. This uniqueness has drawn the attention of researchers worldwide, with each new survey deepening both intrigue and uncertainty. The sheer inaccessibility of the site adds a layer of isolation that heightens the sense of encountering a phenomenon entirely beyond human reach. Recent expeditions continue to record sudden spikes in readings, indicating that these invisible forces are neither static nor fully understood. Even areas that previously appeared stable may experience abrupt changes in magnetic intensity, suggesting dynamic processes at work far below the ice. The causes of these shifts are unclear, though some scientists speculate they could relate to slow tectonic movements, stress-induced mineral reorientation, or interactions between subterranean water and magnetic rock. Regardless of origin, each discovery reinforces the idea that Greenland harbours forces hidden in plain sight, only perceptible through careful measurement and analysis. The persistence of these anomalies underscores that Greenland still conceals forces beyond current scientific knowledge, challenging both prediction and interpretation. Decades of study, the most advanced instrumentation, and repeated field surveys have yet to produce a fully coherent explanation. The magnetic landscape beneath Greenland is a puzzle that stretches over thousands of square kilometers, with variations that defy expectation and interpretation. Each measurement reveals new irregularities, creating a patchwork of evidence that hints at a deeper, unknown structure lurking beneath the ice sheet. Even historical records of early geomagnetic studies in the Arctic fail to account for the sudden spikes and irregular shifts recorded today, emphasizing that these forces have eluded detection for generations. Even when every sensor is accounted for, Greenland's magnetic distortions continue to bend perception and data alike, leaving the interior a realm of unresolved mystery. The secret abandoned bases of the Cold War Arctic. Scattered relics of Cold War-era military installations in Greenland continue to puzzle historians, with equipment and records disappearing under circumstances that remain unexplained. The remnants are often little more than skeletal structures, rusting machinery and frozen storage containers half buried by time and snow, yet they hint at a network of activity once vital to the US. Military's Arctic operations. Some foundations still show traces of insulated corridors, while concrete platforms bear faint markings of instrument placements that no one fully understands. Despite decades of study, much about the base's full purpose and operational scope remains unclear, leaving both scientists and historians to speculate about what has been lost to the relentless isolation of the far north. Every expedition uncovers fragments of communication lines or tool caches, yet no single survey has ever pieced together a complete picture of the operations conducted there. Engineers and military planners designed these bases to host radar systems, communications arrays, and early warning sensors, forming a silent network meant to detect potential threats from distant regions. These installations were intended not only for observation, but for rapid response coordination, capable of feeding intelligence back to command centers thousands of miles away. Archival plans reveal schematics for power generators, living quarters, and observation towers, yet many documents remain classified or destroyed, leaving only partial insight. Maps from the period show a scattering of outposts along Greenland's coasts and interior plateaus, each strategically placed to maximize coverage of the Arctic horizon, yet many details about their construction and operational priorities were classified, leaving gaps that remain difficult to reconstruct. The combination of secrecy, harsh conditions, and incomplete records has produced a historical puzzle that continues to frustrate even the most meticulous investigators. Construction teams faced relentless challenges in moving materials, assembling buildings, and maintaining operations while keeping the installations functional in extreme isolation. Crates of prefabricated structures were transported by ship, aircraft, and occasionally over treacherous ice paths, requiring careful coordination in a climate where even small errors could have catastrophic consequences. Tools, spare parts, and fuel had to be stockpiled with precision, yet storms, shifting ice, and sub-zero temperatures often delayed shipments or damaged equipment, forcing personnel to improvise solutions that remain only partially documented in surviving records. Accounts from personnel recall temporary shelters collapsing under snow, fuel caches frozen beyond use, and improvised heating solutions to prevent water systems from freezing, giving a vivid sense of the daily struggle to sustain these remote operations. Records indicate that many bases were abandoned quietly, leaving behind structures and machinery that gradually vanished beneath layers of snow and accumulated debris. Some were closed after strategic priorities shifted or technologies advanced, while others were simply too costly to maintain in such an unforgiving environment. Decades later, what remains are scattered buildings whose roofs have collapsed, storage facilities with doors warped by frost, and heavy equipment partially encased in ice, giving the impression of sudden disappearance rather than planned decommissioning. Archaeological surveys have identified patterns in debris fields, suggesting that some materials were intentionally left behind, while others appear haphazardly discarded, leaving unanswered questions about the decisions made during abandonment. Derelict vehicles, frozen machinery, and poorly documented storage facilities suggest that operations once conducted at these sites were more extensive than official reports acknowledge. In several locations, tracked vehicles are still partially intact, their original paint faded, and their metal corroded, but their exact functions remain unknown. Crates labelled with technical markings offer only tantalising clues about what was transported, and occasionally remnants of communication equipment or radar components appear in places that defy conventional explanations for their placement. Some vehicles show signs of repair attempts long after main operations ceased, hinting that personnel may have intermittently returned or that parts were scavenged for other purposes, a detail still under investigation. Satellite imagery and aerial reconnaissance have revealed portions of these installations, yet multiple sites remain unmapped, their details concealed from both public and scientific scrutiny. High-resolution photos sometimes capture rectangular foundations or rusted frameworks barely emerging from the ice, but the full extent of each base is often obscured by snowdrifts or cloud cover. Expeditions attempting to ground truth these locations report that the installations often differ from official schematics, raising questions about undocumented expansions or experimental projects that were never publicly acknowledged. In some cases, unusual patterns of shadows and reflections suggest the existence of underground or partially buried chambers, further complicating efforts to determine exactly what lies beneath the surface. Field teams occasionally encounter instruments that are displaced, missing components, or installed in locations inconsistent with original blueprints, deepening the sense of mystery. In one instance, a weather monitoring array was found several hundred meters from its recorded coordinates, suggesting either relocation or drift due to environmental forces, though no corresponding explanation exists in the historical logs. Similarly, some storage units appear to have been modified on site, incorporating technologies that were classified at the time, leaving investigators to puzzle over their intended applications. Detailed photographs reveal rusted connectors and broken wiring that may hold clues to the operation of unknown systems, hinting at projects that may never be fully understood. Maintenance logs and archival records provide only partial insight, often omitting details of supply chains, personnel rotation, and the full inventory of technological equipment. Many of the documents that survive are fragmentary, written in shorthand or partially destroyed during the abandonment process. Logs mention routine inspections, fuel shipments, and equipment testing, yet they stop abruptly in some cases, leaving long gaps where no record exists of what occurred during the final months of occupation or the first years of abandonment. Cross-referencing these partial logs with oral testimonies from veterans sometimes provides small insights, but the full operational picture remains elusive, leaving more questions than answers. Investigations have noted subtle electromagnetic and acoustic anomalies near some installations, hinting that remnants of the bases may still influence their surroundings in unexplained ways. Technicians visiting these sites have occasionally recorded faint signals that cannot be easily traced, suggesting that some devices may have been left powered, malfunctioning, or even affected by the surrounding metal structures in ways not fully understood. While these anomalies are minor and do not pose a threat, they add an unsettling layer to the mystery, as if the bases continue to speak in a language only partially understood by those who study them. These faint signals persist even in locations long thought to be cleared of any functional equipment, hinting at residual effects that challenge conventional explanations. These abandoned outposts serve as stark reminders of human ambition in extreme conditions, preserving fragments of Cold War operations that defy complete reconstruction. Each broken building, frost-covered instrument, and misplaced vehicle hints at the immense logistical effort and technological experimentation that occurred in the high Arctic, yet their full stories are lost. The bases are at once monuments to ingenuity and cautionary tales about the challenges of projecting human activity into environments that refuse to remain still, blending history with a quiet, persistent uncertainty. Photographs of partially collapsed structures and frost-ridden corridors reveal ghostly impressions of human presence, emphasizing how quickly time and environment can erase even the most carefully constructed outposts. Decades of research have yet to fully uncover the scope and purpose of Greenland's secret military sites, leaving gaps that continue to intrigue both scientists and historians. Despite careful study, modern technology, and international interest, there remains no comprehensive record of how many bases existed, how fully they were equipped, or the extent of the experimental programs that may have taken place. Each expedition uncovers fragments, each satellite image reveals partial outlines, yet the collective picture of these Arctic installations remains incomplete, suspended somewhere between documentation and speculation. The persistence of these unknowns continues to challenge both historical and scientific approaches, leaving the human story entwined with an enduring Arctic mystery. Buried within rusting metal and frozen memories, Greenland's Cold War bases hold secrets that whisper across time, daring anyone to unravel the full truth. The unknown future locked inside Greenland's ice core records. Columns of ice extracted from Greenland rise like frozen time capsules, each layer holding chemical traces and atmospheric bubbles that preserve events scientists cannot yet fully explain. Drilled deep into the ice sheet, these cores carry the weight of hundreds of thousands of years of Earth's climatic history, from minor seasonal variations to massive environmental upheavals. Within their transparent layers, particles of dust, trap gases, and microscopic organisms lie preserved in astonishing detail, waiting for researchers to decipher their hidden narratives. Yet despite decades of study, each new analysis seems to uncover puzzles more confounding than the last, as if the ice itself resists complete understanding. The cores serve not merely as records, but as silent guardians of mysteries, preserving fragments of a past that is intimately connected to an uncertain future. Delicate bands within the cores record centuries of snowfall, dust deposition, and trapped air, each stratum a silent witness to the rhythms of a changing planet. Seasonal variations are etched in pale layers, marking annual cycles that repeat with remarkable consistency, yet occasional irregularities disrupt these patterns, hinting at environmental forces not fully accounted for in current models. Bubbles of ancient air are frozen in time, containing precise ratios of carbon dioxide, methane, and other trace gases that provide a direct window into atmospheric conditions long vanished. In some cases, volcanic ash or windblown sediment is embedded with striking clarity, offering insights into distant eruptions and atmospheric circulation patterns. These natural archives are both meticulous and enigmatic, revealing much while concealing even more. Unanticipated fluctuations in methane and isotopic compositions appear in certain layers, leaving climatologists puzzled over what could have triggered these abrupt anomalies. Some spikes occur simultaneously with known volcanic eruptions, while others appear without any corresponding event in the historical record. In rare instances, methane concentrations soar to levels far beyond what would be expected from natural variability, raising questions about the potential involvement of permafrost release or under-ice microbial activity. Each discovery provokes debates among researchers as they attempt to reconcile these anomalies with broader climate models. These unexpected features hint at processes that remain hidden beneath the surface of our understanding, encoded in the ice like messages from a time before modern observation. Sections of ice reveal warming and cooling episodes that unfolded within decades, episodes so sudden that they challenge conventional theories of gradual climate change. During these periods, temperature proxies indicate shifts as dramatic as several degrees within a span that is nearly imperceptible in geological terms. The abruptness of such events defies the gradualistic assumptions underpinning many climate models, forcing scientists to reconsider how energy is stored and released in polar environments. Evidence from Greenland's cores suggests that even relatively minor triggers, perhaps a change in ocean currents or atmospheric circulation, can initiate cascading effects that ripple across ecosystems and continents. These lessons from the ice remain both intriguing and deeply unsettling, revealing a planet more volatile than contemporary understanding often assumes. Minuscule particles and preserved microbial life offer glimpses into vanished ecosystems, suggesting shifts in ancient environments that remain only partially understood. Pollen grains, fungal spores, and microorganisms are trapped with extraordinary fidelity, providing snapshots of local biotic communities and their responses to climate change. The presence of salt, dust, and soot layers hints at distant fires, volcanic eruptions, or shifts in sea ice that would have affected human and animal populations long before recorded history. Even in layers dating back hundreds of thousands of years, these tiny remnants persist, creating a biological narrative that intertwines with the chemical and physical record. They hint at complex environmental interactions that are only beginning to be understood and which may hold lessons for the present and future. When cross-referenced with distant ice cores, Greenland's records sometimes diverge sharply, hinting at localized or previously unrecognized events that complicate global climate reconstructions. Comparisons with Antarctic cores reveal patterns of synchronous change in some instances, yet in others, Greenland's ice tells a distinct story, suggesting the influence of regional phenomena such as shifts in Arctic currents, atmospheric blocking, or sudden glacial melt events. These discrepancies challenge assumptions that climate change is uniform, highlighting the nuanced interplay between local and global forces. Researchers must balance these variations carefully, considering how singular events in one region might reflect broader climatic processes or isolated anomalies that defy explanation. Repeating sequences of irregular chemical and dust patterns emerge in unexpected intervals, defying classification and suggesting hidden cycles in Earth's past climate. These sequences hint at processes that may have operated on scales and rhythms not yet identified, from episodic glacial surges to mysterious atmospheric perturbations. Statistical analyses have attempted to correlate these irregularities with known environmental events, yet many patterns remain unexplained, appearing as enigmatic signals embedded within the broader record. Some layers show rhythmic deposition of fine particles, while others contain abrupt spikes, creating a complex mosaic that continues to challenge interpretation. The ice preserves these signals with perfect fidelity, leaving modern science to grapple with evidence of forces that may remain beyond comprehension. Scientists attempting to model future climate scenarios using these ancient records are confronted with limits, as unpredictable past extremes resist easy extrapolation. While ice cores provide invaluable data for understanding long-term trends, the unexplained anomalies and abrupt transitions caution against overconfidence in predictions. Models that assume smooth, gradual changes fail to account for the sudden environmental swings clearly documented in the ice. As a result, projections for the Arctic and global climate are necessarily provisional, constrained by gaps in knowledge and the lingering spectre of unknown events. Greenland's cores remind researchers that Earth's systems are simultaneously observable and elusive, offering both clarity and mystery in each frozen layer. The physical challenges of extracting and preserving ice that spans hundreds of thousands of years are immense, and even minor errors can obscure vital information. Drill contamination, melting and mechanical stress threaten the integrity of cores, and laboratories must maintain strict protocols to ensure that isotopic and chemical signals remain intact. Even after careful preservation, minute shifts in temperature or exposure to light can alter fragile layers, making it a meticulous and cautious endeavour. These technical hurdles underscore the fragility of the knowledge extracted from the ice, where each slice represents an irreplaceable fragment of Earth's history, and where a single misstep can erase centuries of environmental memory. Detailed analysis sometimes uncovers anomalies that remain inexplicable despite modern instrumentation, leaving gaps in understanding that persist across generations of researchers. Unusual chemical ratios, trapped air compositions, and particulate layers occasionally appear without precedent or clear explanation, provoking intense debate. Even with cutting-edge spectroscopy, mass spectrometry, and radiometric dating, some signatures remain ambiguous, challenging assumptions about past atmospheric composition and forcing scientists to consider mechanisms not yet recognized. Each anomaly acts as a reminder that, while the ice is a meticulous record keeper, it holds secrets that may not yield easily to human inquiry, preserving questions alongside answers. Each newly drilled core reveals patterns of past upheaval and enigmatic signatures, emphasizing that the ice holds more questions than answers, and that some mysteries may endure indefinitely. Researchers document subtle layers of dust, microfossils, and chemical markers that hint at climatic events never recorded elsewhere. These discoveries often prompt more questions than conclusions, challenging assumptions about environmental stability, Arctic processes, and global interactions. Even the most detailed surveys leave fragments of uncertainty, as if the ice anticipates the limits of human comprehension. Greenland's cores stand as frozen manuscripts, chronicling both known and unknown chapters in Earth's history, waiting for interpretations that may only come generations from now. Locked within these frozen layers, Greenland's ice cores conceal a history that could reshape our understanding of both past and future,